Hello, testing. Can you hear me? If you can hear me, can you type in the chat box below? We are still testing the sound. If you can hear me, please type in the live chat box below. Hello, testing. Can you hear me? If you can hear me, can you type in the chat box below? Okay. So it's almost 10 o'clock. We have about 5 minutes to go. So I'm still trying to set up this sound to make it as clear as possible. Okay. So it's almost 10 o'clock. We have about 5 minutes to go. So I'm still trying to set up this sound to make it as clear as possible. Okay. Okay, so if you have any issue, you can just type in the box below and I'll try to fix it before we go live. Like if you can't access the notebook, I'm going to copy the link to the notebook and paste in the comment section of YouTube live. So if you have any issues, please use the chat box. So I'm going to get the link now. The link is going to be a view only link for now, so I'll talk more on that later. So I'm going to get the link now. The link is going to be a view only link for now, so I'll talk more on that later. So it's 10 o'clock, okay? So let's go live. Come. Yeah, hi. Okay, so just gonna set this camera properly. Yep. Okay, blackboard. Alright, so it's 10 o'clock. So welcome to this class, deep master class in deep neural networks, and it's quite a thing of joy that you have taken out time to attend this class, even though with everything going around in the world right now. So while we hope and pray that things get better, I believe we still need to upskill ourselves and better ourselves. Okay, so hence this master class. So you can join from anywhere in the world, and share the links with your friends, and they can always join the YouTube live. Okay, so we won't be wasting much time, so I'm just gonna go straight to what we have for today. Okay, so masterclass in deep neural networks by Odegua. Now I'm monitoring the live chat. Okay, someone is saying there's background noise. Yeah, I'm trying to fix that. I don't know, probably just let me know if you think the sound is better. Okay, just let me know. So I'll be monitoring the live chat from time to time, so if you have any issue, you can always put it there and we'll work on that. Okay, so back to this masterclass. Okay, so it's a masterclass in deep neural networks, and okay, so you're welcome to this class. Now before we go further, some important information I would like to share, how the class is structured. So when I sent out this form, I actually had a target for advanced people in deep learning, people who have done a couple of things in deep learning. But I think from the result of the form, majority of people are actually new to deep learning. So I'm going to try to go down and be as simple as possible. But you just have to know that this class is going to have lots of theories. Then we're going to go get the code. So the class structure is actually little theory. Then we write the code to back it up. And then at the end of the class, we have this big picture where we put everything together. Okay, so he said, yeah, it's clear now. Okay, so great, we can go on. Then you can ask questions in the live chat session. Like I said, I'll be monitoring the live chat session. Someone is still complaining about the background noise. I don't know. Okay, I'm going to reduce this a bit. I hope it's better. Okay, so you can ask questions in the live chat session. I'll answer every 20 minutes. And the recordings for this class will be available at least 48 hours after the class. So you can take your time. If you don't understand something, like Professor Andrew Eng will say, don't worry, you'll get it later. So you can take your time after the class. You can go back, use the recordings, and try to better yourself. And I'm always available for questions, so you can always ask me questions and the rest. Okay, so as you can see, I'm under this Data Science Nigeria body, and I have to briefly tell you about Data Science Nigeria. I believe most of you already know about Data Science Nigeria, because we're doing a lot in the Nigeria AI and data science ecosystem currently. Okay, so Data Science Nigeria is a non-profit driven by the vision to be the world-class artificial intelligence and research center here in Nigeria. And we deliver high impact research, business use case, and relevant AI startups. So you can see our founder, Dr. Bayo Adekambi, is the CTO at MTN Nigeria, and is a chief visionary at Data Science Nigeria. So you can actually learn more by visiting the website here. You can learn more about Data Science Nigeria. So, okay. And about me, my name is Odegua, data scientist at Data Science Nigeria. Actually one of the best places to work in Nigeria right now. hands down, and I'm not joking. Because the people here, they are world class. You know, the environment is friendly. It gives you room to grow, and since I've been here, like, that's really been great for me. So watch out for those guys. Okay, so you can follow me on Twitter, Rising Developer, on LinkedIn, and that is my official email. Okay. So okay, great. So now I think we're getting into the content for today. So for the part one, we're going to have two parts because this is going to stretch. Great, everything is nice. Work on the background noise is not clear. Oh, it's not clear. I'm going to try and I think maybe it probably is your network over there. Sorry for the delay. I'm just going to try and increase this volume a bit. Okay, I hope it's better now. Okay, so the content. Now, what are the contents? We have a brief introduction to artificial intelligence because deep neural networks are actually under artificial intelligence, as we'll get to see later. Then we'll talk about deep learning. What is deep learning? Then we'll talk about intro to neural networks. Why are neural networks popular now? Because they've been around for a really long time. So why are they very popular now? Then also we'll talk about building a neural network from scratch. What are the tools that you'll be using? And we also have to frame a problem because we have to solve a problem using this neural network. Okay, and we also look at the layers of a neural network. It's okay. The live chat is distracting me, so I'm going to try to focus. Every 20 minutes, I'm going to check that. Okay, so we'll talk about the layers of a neural network, the weights and biases, activation function, loss functions, going forward propagation, back propagation. I know most of these things may sound strange or sound new to you, but I'm going to try and explain them clearly to you. Then how to train a neural network and making predictions. So that's the part one. Okay. Then for the part two, we are going to reduce this a bit. Okay. So for the part two, we are going to create a neural network class. Then actually this is more of like standardizing our neural network. So we are going to follow the APIs of maybe sklearn and Keras and try to copy their API and make our neural network standard. Then we'll test the network. Then I'll talk about some extra improvements that you can do, and then we'll look at summary and conclusion. Okay, so great. All right, let's get started. And remember, if you have questions, you can always use the live chat box. Okay, and in the chat session and also in the mail I sent yesterday, if you have the mail, I actually shared a link to the Google Colab notebook. Okay, so I gave everyone view access, so you can actually see me as a live code because we are going to be live coding today. So you actually see me as a live code, and you can actually create a new notebook and maybe live code with me, or you can wait after the class, then you can go over it again. So after the class, you can actually make a copy and save. So you can actually make a copy and save in Drive. So but for now, you can just view and watch as I live code. So you can check the chat session and get the links. Then if you also registered, you can check your emails. I sent out the links yesterday. Okay, so let's go back to our webinar content. Okay, so all right, so we're starting now. So first of all, a brief intro to artificial intelligence. Now we've all heard the word artificial intelligence, and I believe coming to this class, I believe you know one or two things about artificial intelligence, so I'm not going to spend much time here. So what is artificial intelligence? So AI simply means it's simply the intelligence shown by machines and computers and their ability to mimic humans in areas of learning and problem solving. Now the idea here is that humans are super intelligent, so and there are some things that we do easily that if you try to teach a machine or you try to program a machine to do it, it's going to be very difficult. Take for example a baby. a baby that learns to differentiate between a cat and a dog. Okay, so for example, if you show the baby pictures of cats, show the baby pictures of dog, and you keep telling the baby, this is a cat, this is a dog, this is a cat, this is a dog, you find out that with time, the baby starts knowing how to differentiate the cat from the dog. Okay, so basically, we humans, we are good at things like face recognition, image recognition. We can easily recognize and differentiate one object from another. Okay, so but trying to teach or program a computer to do that is very difficult, because what are the possible rules you are going to write? It's going to be very difficult. So we need to like come up with a way that computers should be able to automatically learn on their own. Okay, so I think that's the idea behind artificial intelligence. So we want to try and replicate intelligence in human on machines or in machines. Okay, so that's the idea behind AI. So AI is not just about robotics or the Terminator. Like most people, when they hear about AI at first, they think deadly robots and the rest. So AI is much further than that. Okay, so that's the idea behind artificial intelligence. Okay, so now under this artificial intelligence, you have different feeds under it, different sub feeds under it. So, and deep learning is actually one of them. So if you notice, the title of our class is introduction or master class in deep neural networks. So what exactly is deep learning? Now the idea is that deep learning is a machine learning technique. So machine learning is like this broad feed over. After artificial intelligence, you have machine learning. Then under machine learning, you have sub feeds. So deep learning is actually one of that sub feeds. Okay, so it's a machine learning techniques, meaning you have other techniques, but deep learning is a type of it. Okay, so you have maybe your decision trees, you have your neighbor method, and then you have deep learning method. Okay, so it's a machine learning technique that is is an efficient way of learning that relies on big data. We have features that can help a machine map input to output is automatically extracted from layers of neurons. Okay, so the idea behind deep learning is to stack what we call neurons, together. Okay, so and consistently use these neurons to extract features from data. Now, most traditional machine learning algorithms like decision trees, like your neighbor, support vector machines, and the rest, what they do is they like you have to extract data from it. Okay, maybe manually extract some features from it, then pass it to your algorithm to do the learning. But deep learning it makes things easy for us because there are some kind of data that you cannot actually extract the features. Okay, so if you try extracting features like images, for example, you want to try extracting features from images, it's going to be very difficult. Okay, so can we do this automatically? That is the idea behind deep learning. Okay, so it's a technique that can automatically extract features from data and be used to make predictions. Okay, so we move from, now you can see that this is kind of like an hierarchy. We're going from artificial intelligence to machine learning, and under machine learning we have different subfields under it, and of which deep learning is a type. And under deep learning we have the most popular algorithm, which is called the neural networks. Okay, so this is going to be our main focus for today, neural networks. Okay, so the idea behind neural networks is that they are composed of building blocks called neurons. Okay, so if you look at this, I think I should use my pointer. Yeah, so if you look at this is called a neuron. Okay, so I think most people like to draw this correlation between the human brain and artificial neural networks, but I think I'll just go straight to the point. Neural networks are just composed of neurons. These are neurons. So, and each neuron performs a mathematical function. Okay, so for example, if you look at this deep learning, now you see each of these. Now you see these are called neurons or nodes. Now each of these nodes is connected to the next node. You can see it's passing information from here to the next, from here to the next, from here, and so on. That is why it's called deep learning. So you have layers upon layers upon layers of that. Okay, so let's go back to this guy. Okay, so each of those nodes is as if, okay, we are zooming into a particular node. So each of those nodes actually performs a mathematical function. That is, it takes input data. You can see we have x, all these x1, x2, x3. These are input data. If you have a fixture, for example, like age, salary, and maybe years of experience, those are your input features. So you're going to pass those input features to each of the node, to this node. Now this node performs what we call a weighted average. Okay, so each of these nodes, for example, I think I should probably use a board. I don't know if you guys can see the board clearly, so I'm going to, okay, I think this is better. So each, for example, if you have age as a feature, you have for example years of experience, then you, okay, so these are input features. So for example, so we take this input feature and pass them to the first node. The node is going to perform two functions. It's going to perform a weighted average. Weighted average in the sense that it's going to, maybe for example, I want to try and predict salary, for example. So salary is my output I want to predict. Okay, I think I'm going to, yeah. Okay, I think it's better this way. Okay, so for example, I'm trying to predict salary. Okay, so each of these features can help me predict the salary of the person. All right, I'm going to take this here a bit. All right, so I think it's better that way. Okay, so now what the node is going to do is that it's going to take each of this feature and it's going to assign a weight to it depending on how important it is. So the weight basically tells you how each of these feature is important. So for example, I'm going to add say school, for example, if the person went to school or not, as a feature that's going to go into this. Okay, so for age, I'm going to assign a weight. So weight, let me say weight of age. For years, I'm going to assign a weight, and for school, I'm going to assign another weight. So I'll just call this W1, W2, and W3. So the weighted average takes the age, which is age, times its weight, plus the years times its own weight, plus the school times its own weight, and add everything together to get a weighted average here. So basically these weights are very important because they tell you how important these variables are. So for example, you might be surprised that school and years are important features when you're trying to predict salary. So if you look at the weights of your neural network that your neural network is going to generate, they are going to be actually very high. Okay, so just think of features as the input variable. So if we come back here, you see each of these inputs are going to go into a node and they're going to be multiplied by their own individual weight. So we'll do something called a weighted average, where we take W1 times X1 plus W2 times X2 plus W3 times X3, and we sum everything together. Okay, so now the next part, I said that the neuron actually performs a mathematical function. Okay, so the next part of that function is going to take this weighted average, okay, and pass it through something called an activation function. Okay, so this activation function is also called a non-linear function, because basically if you don't pass this weighted average through an activation function, you're basically doing what is called linear or logistic regression. Why? Because these are all linear combinations. Okay, so basically if, for example, let's go back to this slide. So you see that this is a feature, this is a feature, this is another feature. So for example, this is age, salary, and years of experience, and you can see these are all other nodes. So it's going to take each feature, pass it to this is going to go to this. So each of them are going to have their own weights. Okay, and those weights are one of the most important things that we are going to be learning in neural networks, because they actually make up what your neural network is going to predict. Basically, the job of deep learning or neural networks is just to look for the right weight If you can get the right weight, you can predict any of these functions. Okay. So we have this again. All right. So remember, each node of the neural network takes an input feature, multiplies it with its own weight. That's called the weighted average. Pass it through an activation function, which we are going to talk about later. Okay. Then brings out an output. Okay. So imagine stacking lots of these together. Okay. So meaning each of these, like this guy is going to perform its own weighted average, this guy is going to perform its own weighted average, and it keeps passing it forward. Once this guy is done, it passes it to the next guy. Once this guy is done, it passes it to the next guy. So you can see we're going to have stacks of these, lots of these individual nodes performing their own mathematical function, and we'll keep adding them together and passing it on to the next one. Okay, I think it's more than 20 minutes. I'm going to look at the chat. Okay, I see a question from Maxwell. Maxwell is saying, who assigned the weights to the variables? Great questions. Okay, so now the weights are going to be assigned or are going to be learned by the network, because in fact that is the process of learning. The process of learning in a neural network is just to learn these weights. So at first, when you pass in your data, you are going to assign random weights to each of these weights. You are going to assign them randomly. So as the network continually learns, it's going to keep updating the weights by itself. So for example, I think I'm going to come back to the blackboard here. Okay, I believe we can all see this. Okay, so basically the weights are going to start at random. So for example, I might give this weight say 0.1, I might give this 0.3, then I might give this say 0.7. okay, now you can see that school has a higher weight than this guy and this guy. So it's trying to tell you that, for example, probably school is more important than the others, but we don't know yet. So what the neural network does is to do the weighted average, pass it to this guy, pass it to an activation function, make a prediction. So for example, if the true value of the salary is say $1,000, for example, and the neural network, after doing the weighted average, passing through the activation function, it got say $600, for example. It's predicted $600, for example. So what you are going to do is compare this prediction with the original prediction. So you can subtract and see, okay, how far is this guy from this guy. So by knowing how far, you know your error. So you know, okay, maybe I have to increase my prediction or I have to decrease my prediction. So we use something called the backpropagation algorithm to after comparing the error, you can come back and adjust your weights. So the neural network will automatically come back, looking at the error, it will adjust its own weight at the beginning and make another prediction. So for example, if it adjusts the weight to, let's say, 8, these are just random numbers, so then it makes another prediction of let's say 900. It compares again and see how far am I. Okay, I'm not too far. Okay, so maybe adjust the weight just a little. So this back and forth is what a neural network does. So it's first you initialize random weights, make your weighted average, pass through an activation function, make a prediction, check the correctness of the prediction, then adjust the weights behind. Okay, we are still going to talk more about this as we go, but if you have any other questions, you can still put it in the chat. Okay, no question yet. All right, so remember, we have this. So this is the basic building block of a neural network. So if you see stacks and stacks of neural networks, these are just what each node is doing. Each node basically performs a mathematical function where it does a weighted average of its inputs and their weights, passes it through an activation function. Okay, and also I would like to also mention that there's something called a bias. I was supposed to add that here. I think there's an error in my slides. I'm going to make the correction. Okay, so there's something called a bias. Bias is like a base term. So for example, if you are trying to make predict salaries, for example, I don't know why I'm always using salary, but assuming you're trying to predict salary, for example, now you might decide to have a base salary for everybody, irrespective of the age, the class, and whatever. You might decide to have a base salary for everybody. Say for example, everybody, whether you are, no matter your age or what, you must have a base salary of say $500. Okay, for example. So that base salary is called your B. So the B is like a constant; it's going to be there. So meaning you add it to each of your calculation. So after doing your weighted average, you always add the B, the bias. It's called the bias. You always add it to there. Oh, someone is saying the writing is not legible because of the reflection. Okay. So maybe I'm going to do less writing because it's not that clear. Okay. All right. So I'm going to do less writing. So, but just understand this. Okay. So this is the building block of neural networks. So if you can actually create a single node or a single neuron like this, you can add them together and you have your neural networks. Okay. So now another question is why are neural networks very popular now? Because I think neural networks are what made AI very popular. Because from time to time you hear in the news AI powered this, AI powered drone, AI powered food, AI powered this, AI powered search, and the rest. It's actually most of these products actually became popular because they are now using neural network. But the thing is that neural networks are not new. Okay, they've been around for a really long time. Okay. Okay. So they've been around for a really long time, but they had some problems back then. So some of the major problems they had was that it was difficult to train, in the sense that there were not enough data back then in the 90s. So, but today we have lots and lots of data. Okay. Someone said my voice is low, so I'm going to try and increase that a bit. Okay. So I was talking about the problems with neural network earlier in those days. So we have, it was difficult to train. It needed a huge amount of data, which was a big deal back then, and computing power was still low and expensive. So currently we have more data. The world has gone digital, so we have more data. We have access to cheap compute power. If you can't train your models locally, you can actually go to the cloud and rent a cheap computer. So compute power is now relatively cheap to get, and also there have also been improvements in algorithms. So okay, so why they are popular is because actually they work. Neural networks, it works actually. So for tasks like image recognition, voice recognition, in fact any unstructured tasks where you don't have tables and columns as your data, maybe you have data in image format, in sound format, neural networks actually work very well. So that is why they are popular. So most of the time you see people say, okay, if you have a problem, just use a deep neural network. Although they are popular and they are good at those kind of tasks relating to text, images, sounds, and the rest, they are not that perfect. Okay, when it comes to other tasks like structured data. Okay, that's why you still use your traditional machine learning algorithms. Okay, so that's one of the reasons why neural networks are popular now, because they actually work. And also an important thing is that they can automatically extract features from data, because if you're going to sit down and extract a feature from an image, it's going to be very difficult. Okay, I don't know if that is even possible. It's possible, but it's going to be very difficult. So but neural networks actually automate this and makes it possible. Okay, all right. So now building a neural network from scratch. Now people will say, why do you have to build a neural network from scratch when you have libraries? There are lots of libraries are available. There's Keras, there's sklearn, there's TensorFlow, there's PyTorch. Why do I have to build one from scratch? Now the goal is not to build a neural network that you are going to use. Okay, I think the goal of this exercise or of this class is to build something that is already existing, but because you want to better understand how it works. So this the idea here is that you are going to learn the inner workings. Why do we initialize? How do we initialize weights? How do we train the network? How do we sample the data? So you're going to learn this low level and inner workings of a neural network to help you better understand how to use these libraries. Okay, so I trust that after this class you are going to like see libraries, deep neural network libraries in a new level, because you are going to know why we use learning rates, why we use an initializer and different stuff like that. So this exercise is actually very good, and I think you should do it at least once in your lifetime as an AI engineer or a data scientist. You should try to maybe implement some of these algorithms from scratch at least once. Okay, it's going to be very, very important. All right. So so that's how we're building this neural network from scratch actually. Okay. So now, what tools are we going to be using? Okay. So we're going to be using Python and NumPy. Now, why am I using NumPy? I said we're going to be building from scratch, so we probably don't need external libraries. But NumPy is going to help us. NumPy is going to help us with matrix multiplication, addition. It's going to help us handle most of the math that we're going to be using. Okay, so that is why I bought NumPy. Okay, so I'm having issues. Okay, fixed. All right. So now let's move on. We're going to be using NumPy. We're going to be using Python. Python, it is easy to learn. Lots of existing packages. There's clean syntax, easy to read. That's a great community. So that's the reason why we're going to be using that. Okay, so let's move on to the problem at hand. All right, so we're going to frame a problem. Now, before we start coding, before we start writing our neural networks, we have to first of all understand a problem or frame a problem. Okay, so the problem we're going to be working on is on breast cancer diagnostics. So we're going to predict if a person has benign or malignant cancer. Now, I think benign cancer is actually a less, I think, actually, how do I explain this? It's actually, both are bad, but benign cancer, according to what I read, it does not spread to other parts of the body. So if someone has benign cancer, the cancer does not spread to other parts of the body. But if you have a malignant cancer, it can spread to other parts of the body. So this is actually way worse than this guy over here. Okay, so now we're trying to predict if someone has benign or malignant cancer. So this is a classification problem. Okay, so we have two classes. So meaning the neural network we're going to build is going to take a breast cancer data set and predict one of two classes if a person has benign cancer or malignant cancer. Okay, so that's the task. Now, so this is the page for the data set. It's hosted on UCI. I think I should go to, I'm going to create. If you go to UCI dataset, just search for UCI datasets on Google. I think that should be the first link, UCI dataset. And yeah, so you have 4 different versions. There's original, there's prognostic. So this is the one we are working on, diagnostics. Okay, so we're going to download the datasets right now. Okay, so you can go there, download the dataset diagnostics. Okay, so this is the dataset page. You can see we have source, dataset information, and the rest. So, but I'm just quickly going to go to data folder, and we have, I think, yeah, we have this data. This is data, and this is the names. So I'm just going to download both of them. So just click. Okay, so I have them here. So let me just quickly open the data. I'm just going to quickly open the data formats now. Okay, that's taking some time. So, but basically, this is in. Okay, I don't think you can see this. So, but just for now, let's but just download the data. So once you download, it's going to come in a data format, .data format. It's not in CSV format. It's going to be in .data format. So after downloading that, what we are going to do now, we're working from Colab, right? So we are going to add it, upload it to Colab. So in Colab, you can actually use this upload button. So I think I have it before. That's why you have all these. Okay. So, okay, now I have it here. So the name is kind of weird. So I'm going to quickly rename this to, yeah, we consider data. Now you can see it's in date.data format, not in CSV. So we are going to have to read this, and someone is asking for the link to downloading the data. Okay, I'm going to add it. I'm going to add the link to the notebook. Okay, so if you have access to this notebook, just come copy it from here. Okay, so the link is there, so you can just click on it and it takes you here. So you're going to download this. The first one, this is yeah, this is it. So you just download this. This is just the names describing the variables and the rest. So just download these guys. The letters are blurry. Oh, okay, I think so. I'm going to kind of zoom in a bit. Yeah, so I think it should be clear now. So I'm zooming in a bit to make it clear. Someone is complaining that the letters are blurry. Okay, yeah, I think it's better now. Still going to zoom in a bit. Okay, should be better now. So this is the data page. All right, so now we're going to read in the data. So I'm going to just import some libraries, import pandas. I don't have access to the notebook. Okay, the notebook, I shared the link. So if you check the live chat, so the Colab link is using access. Oh, seriously? Okay, I'm going to share the link again. So I'm going to make it open to everybody. Okay, so just give me a minute. I'm going to quickly share this. How do I get access to the code lab? Okay, so basically, since people are having the same issues, so quickly I'm just going to share the link again, but kind of surprised that, okay, give me a minute. Yeah, I'm going to paste it. I'm going to paste it on the live chat session. But basically, after the class, everyone is actually going to get the notebook. Okay, so not to worry. But in case for people who are trying to follow me here and live code with me, I'm just going to quickly share this again. YouTube. Sorry for the delay. Yeah, almost there. Okay. I'm just going to quickly share this again. So yeah, I shared that. So Okay, so we have it in the chat session, so you should be able to access it now. All right, so let's move on. So we import pandas, import numpy. What other thing are we going to be using? Matplotlib. I thought you were supposed to give me autocomplete. Yeah, I got that. We're going to be using paths, so we can read in our data. What else? What else? Okay, I think let's work with this for now. If we need any other thing, we're going to import. So we import this. Oh, what's the problem? Oh, sorry. I think I have to cancel. Okay, sorry. It's not directly parts, so you import from path-lib. Import path. Yeah, that's it. Okay, I think guys are complaining that the thing is kind of blurry, so I think probably it's your network. I don't know, it's kind of clear over here, so probably your network. You can change the video quality, but all the same recordings are still going to be available, so you can actually watch this again. Okay, so let's go. So our data is currently here. So we have the breast cancer that we can see. So let's read in our data. So I'm going to just create a path, data path. Can't see the link. Wow. Let's see. I'm going to paste it again. It's clear over here, so I think, yeah, it's probably your network because it's clear to some people. So I just shared the link again. I don't know if you can see it.
Sorry for the delay.
Okay. All right, so let's move on. Reload your notebook. Yeah, if you still don't have access, I think you can reload your notebook and try that. All right, so data part. So we're going to get this data part, copy the parts, and okay, so these are our data set. Okay, so we have that. All right, so now let's read in the data. So now the data comes in like I told you before, .data format. So it's not in CSV format. Okay, so we can still use pandas to read it. So for example, let me just show you. So cancer, I'm going to call it cancer data pd.read CSV, passing the data part. And I'm going to quickly print out the data. Okay, now good. All right. All right, so we have, now you can see the data does not have headers. Okay, and we're actually probably going to need the headers, so we're going to like manually add the headers to it. Okay, so the headers can be gotten from, if you go to the website for the data source, this data that names, the headers are actually there. So we won't waste our time, I'm going to copy it. I saved it somewhere, so I'm going to copy it and put it here. So these are the headers. So we have the ID, which is this guy, clump thickness, which is this, over to the end, and this class, which is the last one. So these are our targets. So you can see we have 2 and we have 4. And from the data description, 2 means benign cancer and 4 actually means malignant cancer. Okay. All right, so let's add the headers to the data set. So we can actually add this guy while we are reading in our data. So we are going to put it up here. Then there's a variable called headers. Yeah, I think so. Yeah, it should be headers. No, not headers, sorry, names. Yeah. So we're passing our headers. All right. So let's run this, okay? Great. So we have our data set with our headers, so you can see. So this is the class variable, okay? All right. So let's look at the class. How many variables are there? So we can dot class dot unique. Okay, probably I'm going to use this method. I think this is more cleaner. Okay, so no problem. Nobody's typing any message. Okay. Dot value counts. Anyone with a link to the notebook can share. It's not showing here. It's kind of funny. Okay, so if you have the link, you can actually just drop it on the live chat, because I think most people. Yeah, that's true. Okay. Sorry for the distraction. So that value counts, let's look at the, so we have 458 benign. Remember I told you from the data set, from the data names, which you can find here, contains information about the data. 458 of these data points are benign cases, and 241 are actually malignant cases. So we are just going to do some basic preprocessing. Now I'm going to change these classes to 0 and 1. Okay, so 0 for benign and 1 for malignant, which is that the person has a malignant cancer. So that's more, that's the negative class. Okay, so I'm just going to quickly map this. So basically this is what we are doing currently, so please take note. We're writing some code to download and prepare the data. Okay, so okay, let's go back here. So cancer df of class, I want to map I'm going to use a map function. So the map function is basically I'm going to map 2 to 0 class and 4 to 1 class. Okay. So okay, going to dictionary. So for 0, I'm going to map it to 2. And for 1, I'm going to map it to 4. All right. So let's run this guy. Okay, so if we check, just going to quickly copy. Sorry. Okay, let me copy this and do that again. Oh, what's the problem? Value counts, there's nothing there. That's weird. Okay, let's see. Oh, that's strange. Supposed to be 2 to 1 and 4 to 2 to 0 and 4 to 1. Okay, it's supposed to be this way. So I'm going to have to run this Excel again to get the data again. Run this, and I have this. Does changing the target variable have any impact on the output? No, it does not. But the thing is that we are trying to structure our problem as a binary classification problem, so 0 and 1. And the output of our network, we want to structure it in such a way that it's going to predict probabilities. Okay, so I know probabilities run from 0 to 1. Okay, when you have 1, that is a yes, and you have 0, that's a no. Okay, so if we structure our target class as having 0 and 1, So our neural network is going to predict probabilities. So when it predicts, maybe for example, is 0.8, so you know 0.8 is close to 1. So it's probably saying that this is going to be a malignant cancer. And if it predicts something like maybe 0.1, then you can say, okay, this is probably going to be benign cancer. So the output of our neural network is going to be predicting probabilities between 0 and 1. So it will be better if we structure our targets in such a way that it can be between 0 and 1. We can actually still use 2 and 4, but at the end, we are still going to have to map 2 to the probability prediction. So better we just, do it from the start. Okay? So I think that was the question. All right, so, okay, great. We have this now. All right, so let's see, what other thing can we do? All the data points are in numeric formats. Okay, so let's see if there are missing values in the data. Cancer df is NA. You can use this function to check for missing value. Okay, so there are no missing values, but from the data page, I think I got it from term values, blah blah blah. Yeah, from the data name, sorry, data folder, data sets description. So yeah, so from this, if you read it, you can actually click this and open it. If you read it, you find out that this class, there's a class called bare nuclei. Bare nuclei has some missing values that were represented with a question mark. They're represented with a question mark. So if you take a look at that class, cancer of let's see, bare nuclei dot, let's look at the values there. So you can see, look at this class, look at this is question mark. So from the data page, it was they replaced missing values with question marks like this, and you can see it's actually a string, and this is supposed to be an integer. So if you look at the type, okay, let's see the type. If you look at the type of the data, the types. Remember, why we are doing all this is that if we are going to be training a neural network to make predictions of this, all our features has to be numerical, okay? They all has to be numerical. And you can see most of them, in fact, all of them are actually numerical, but this feature containing strings. So let's look at the type. Sorry. Now you can see they are all integers except this guy, bare nuclei. Why? Because of this question mark. So what we're going to do is we're going to fill this guy with the mode, the most popular class among all these, and convert this variable to an integer variable. That is the only way we can actually use it. Okay, so what we're going to do, cancer df of I think that's bare nuclei. So what are we planning to do? We want to replace every question mark with, I'm going to replace it with let's say, okay, first let's look at the most popular class, that's the mode. Okay, so I'm going to do value counts. What am I typing? Okay. Alright, so then you can see the most popular class is 1. 1 appeared 402 times, so that's the mode. So I'm going to use 1 to replace this guy here. Okay. So how do we do that? We can use the replace function. So cancer df of bare nuclei is equals to cancer df of bare nuclei dot, there's the replace, dot replace. Okay, so I'm going to replace, what are we replacing? I'm replacing question mark with, so for now I'm just going to represent with the string of 1. Why are we using the mode to fill missing values and not the main? Okay, there are different methods that you can actually use to fill missing values. So I'm just decided to use the mode in this case. So you can actually try the main, but if you are going to be using the main, you have to first convert everything here to integers. Okay, so currently they are in string, and you cannot calculate the string, the mode of a string. So if you're going to be using the main, you can actually first convert these guys to integers, then fill with the main. Okay, so I'm just going to use the mode in this case, so you can actually use any of them. Okay, another question was, why not use build fill? Okay, build fill, backward filling, those are all filling techniques. Okay, so depending on you, you can choose to use any of them. Actually also depends on your problem. Okay, so if you look at this value count, you can see the value of 1 is way higher, 402 classes of 1. So that probably tells you that the missing values are probably going to be in this class. Okay, so using the main is going to skew this, because we have lots of classes that are 1. It's going to actually maybe skew this. So I think using the mode will actually be better. The main would be float also. Yeah, that's also another. Okay, can't find the way to delete this page. Okay, seems like the links can't be shared. I've been sending it and it keeps disappearing. Yeah, I think I was having that issue also, so I don't know. Maybe if I type it, no, I can't type it here. That's gonna be long. So you should be able to access it from your email. So just try and accessing it from your email. Okay, so I'm going to replace this with 1. All right, so let's run that. Hopefully there's no error. Okay, now after doing that, I'm going to convert it to integers. So I'm just going to do that for everything. Dot as type int 64. Okay, sorry, I'm supposed to assign it. Alright, so I have this. Okay, so now let's check again. Cancer df dot d types. Great, so everything is now in integer format. Okay, someone is saying I don't have the email, so I don't know how I'm going to share this now. Okay, so maybe let's see, maybe I should try, what about using machine learning to predict the missing value? Yeah, you can actually do things like that, but the goal of this tutorial is not to teach you pre-processing and filling of data. The goal is to actually create a neural network to make predictions on this. So we're just going to do some basic editing. Okay, copy the link. Okay, sorry, get shareable link. So maybe I'm just, let's see, maybe if I paste it here, you guys can see it and write it. Let's see. That's going to be too long. So maybe I'm going to let me quickly use bit.ly to shorten the link. I don't know, this is going to even open. I'm trying to access bit.ly so that I can probably shorten the link so you guys can type it from the screen. Okay, yeah, okay, so maybe you can probably type it quickly. I'm just going to give us, like, for example, like, so this is the link to the notebook, so please quickly The link from the email works for me. I'm using laptop, not mobile. Yeah, I don't know. It kind of works for most people, but some people keeps complaining that they can't access it. But so I'm just going to give you like 2 minutes to just copy this down. So this is the link. I shortened it. So please write it down. Okay. All right. So moving ahead, I believe you all got this. Okay. Okay. So we were actually okay. So we are done with this. We've converted all values to integers. So what else can we do? I'm going to quickly let's take a peek at the data. Okay, so we have all these guys, yeah, class, okay, 0 and 1. Okay, so let's drop this ID column. ID column looks irrelevant, so I'm just going to quickly drop it. Columns equal to ID. I'm going to use in place true. Alright, so I have this. So now the next thing we are going to do, since our data is already in the format, we all have integer data. The next thing I'm going to do is I'm going to separate the data into train and test sets. Okay, so train and test sets. I'm going to use sklearn for that. We can actually write our own function, but we're just going to use this. I believe it's from preprocessing. Import train test split. Yeah, should be that. Oh, sorry, model selection. Model. I always miss this. I always miss these guys up. Autocomplete. Okay. Import. Yeah, train test split. Okay. So we're going to divide our data into training test, so X test, and test set, Y test. Train test split. So we're going to pass in cancer df. Oh, so before we do that, I'm just going to quickly create the X cancer df and the Y. So I'm just going to quickly create sorry about that. So I'm just going to quickly create our data. So basically I'm dropping a class variable from here and assigning the remaining ones to X. Then I'm going to assign the class variable, which is to Y. Okay, yeah, this should work. Okay, so then I'm going to use X here and use Y here. So we're splitting X and Y. Then I'm going to specify the test size. Let's say 0. We have about 200 and something. So let's say 0.2, for example, percent. Then I'm going to set a random state so that we can reproduce, so that you can reproduce this notebook. Okay. So it seems everybody is okay, no questions. Alright, so let's run this out. Alright, so now let's take a look at our training size, training.shape. Okay, good. 559 by 9. So let's look at our Y train.shape. Okay, so we have 559. Now, there's something very important that we're going to do here. We're going to reshape the Y train. Okay, probably we can do that when we start creating our neural network. because it's going to be expecting a two-dimensional. Our network is going to be expecting a two-dimensional target, which is 559 by 1. Okay, but I just like to quickly do it here. So I'm just going to quickly reshape it here. Reshape one. Okay, I think someone is trying to. Oh, I gave edit access. I'm supposed to give view access, not edit access. Yeah. So I changed that to view access so that we can save this. Since someone was trying to edit it, someone is editing it somewhere else. Okay. Sorry about that. My bad. Oh, cancel. Yeah. Okay. The file was written under that to first save right in that sense. So let's save from file menu. I don't want to save, so let's go on. So I was trying to reshape this guy. Someone is asking a question. What does a train test split do? The train test split splits your data, which is this guy, the data and the target, into training and testing sets. So that is what it does. So why we are doing this is because we want to be able to train our neural network on the training data set and test it using the test data sets. Okay, so that's why we're using the train test split. Now another question was, why did you add dot values to the y variable? Okay, so the dot values actually brings out the variable in numpy array. So if I add the values, it actually returns just the values in numpy format. Okay, so if I return this, it's going to return a pandas series, and I don't want a series, I want it in numpy format. Okay, that's why I did this. Okay, so I'm just going to quickly reshape this here. Okay, cannot reshape 669. Sorry, reshape. We're reshaping the last layer. Okay, so now we have this in two-dimensional format. Any other question? And what determines the type of imputation? What other imputation can you use instead of mode? Okay, I think I've answered that question earlier. I said you can use mean, you can use median. It actually depends on your data. But that's not our focus for this class. Okay. So okay, we have this now. Now our data is ready. Okay, so we can start creating our neural network. All right, so I'm going to quickly create a text. Neural network. Okay, so let's go back to our slides. How can I get access to this on GitHub? After the live stream, I'm going to share this on GitHub. Okay, so we are done with this downloading and preparing the data. Now we'll move on to what we call layers of a neural network. All right. So remember when we talked about this deep learning, I said there are different combination of nodes like this, and each is performing its own mathematical function. So each of these nodes is stacked together vertically and horizontally. So if I have this particular node, this stacked, I have 3 of them in the first place here. This is called a layer. Okay, so this is called another layer. This is the last layer. So a neural network is made up of layers. Okay, so you can have the input layer, and you can have lots of hidden layers. It can be 1, it can be 2, it can be 3. Then you have the final output layer. Okay, so between here and here it gives you the depth of the neural network. That is why it's called deep neural network. Okay, so you can stack multiple of these, and the more deep you go, I think the more complex your network becomes, and the more the higher the kind of functions it can actually predict. Okay, so that is why you have the idea of deep neural networks. So this input layer is actually your data. So that's where your data is coming from. Okay, so you pass in the data. So each of these nodes is actually a feature in a data set. Okay, so in our case where we have, where do I have that? In our case where we have 9 features, okay, so we have 9 features here. That means that we're going to be having 9 of these in the input layer. Okay, so we're going to be having 9 nodes representing each feature in the input layer. Okay, so we pass. Okay, so people are asking why I did a reshape. Okay, so I did a reshape. Okay, I think somebody answered that. Yeah, did a reshape so that we can have it in 2 dimensions. So it's needed because if we are building the neural network, we're going to be making some matrix multiplications. So your your target has to be in 2-dimensional format. Okay, to help us when we are coding our neural network. Okay, that was why I did the reshape. Okay, so don't worry about that. I will explain further. Okay, so basically this is a 3-layer neural network. I know somebody might say, okay, why is it a 3-layer neural network when we have when we have 1, 2, 3, and 4. No, you don't count the input layer. So the input layer is where your data is coming from, so you do not count it. Okay, so meaning we're going to have 1, 2, and 3. We're having 3 layers in this network. So we can decide to have 1, we can decide to have 2, we can decide to have 3, any number that you prefer. So the layers is just a collection of nodes at different stage of computation. So once your input passes its feature to the first hidden layer, so this node performs its own weighted average, pass that weighted average to an activation function. This second node performs its own. Now you can see each of the feature is going to each of the node. So it's called a fully connected neural network. Why? Because each feature, you can see this one has 1, 2, 3, and 4. So each of the feature is going to each of the node. So each of the node is performing a mathematical function, which is just a weighted average, and then passing that weighted average through an activation function, which we are going to talk about later. Okay, so this is layer 1, this is layer 2, this is layer 3, which is the output layer. Now you can see the output layer is going to represent the number of classes or what you are actually trying to predict. Okay, so now you can see this output layer we have just 1. So the idea behind output layer is that if you're going to be predicting, say for example 3 classes, you're going to have 3 output nodes. If you're going to be predicting 2 classes, you can have 2 output nodes, but you can also use 1 output node. Why? 1 output node in the sense that you're going to be predicting probabilities. Why? Because if you predict 0.2 as a probability in your output node, that can be taken as negative prediction. Then if I predict something that is higher than 0.5, for example, that can be taken as a positive prediction. So you can use just 1 node to predict 2 classes. Okay, so that's possible. So that is the layers of a neural network. So meaning our network is going to have layers. Okay, but we are going to start simple, because the deeper you go, the more complex your network becomes, the more complex your weight becomes, and it is more difficult to calculate. So we're going to do a very simple, just 2-layer neural network in this class. Okay, so please take note of that. Question, please, can you save this, the live video? Of course it's going to be saved, don't worry, it's going to be saved. After the class you are going to have the video. The notebook, is it responsive? You are not supposed to be editing the notebook. The notebook is just for you to view. Okay, so please just view it. After the class I'm going to actually share it. Alright, so let's move. So talk about the layers already. Now you can see if we zoom in on, for example, just this single node, for example. Okay, so you can see that each of these feature inputs is going to that single node, and they all have their weights. So it's going to perform the weighted average just like I have said. So each node acts as a neuron and performs calculation on the data passed to it. So once it is done with that calculation, it's going to automatically send its output to the next data or to the next node. Okay, so this is the weighted sum. Now we can take this x1, x2, x3 as all the inputs and put them into an array. Okay, so that is represented by x here. So x is a combination of 1, 2, and 3 features. Then the weights which is W1, W2, and W3, we can take it to its own array. Okay, so if we are going to be doing a weighted average, we can just use matrix multiplication. That is why we are using numpy. So instead of trying to do this individually using x1 times this plus s2 times this plus s3 times this, we can stack them into arrays and do the multiplication at once. So W here, sorry about that. So W here actually represents all the weights, and X here represents all the input features. Now remember that bias I told you about, you're also going to add it. So the weighted average is simply the W times X plus B. Okay, so this is going to be a dot product. Remember, dot product is simply saying this times this plus this times this plus this times this. Okay, so please take note. Question: what determines the number of layers you would have? Oh, the number of layers is depending on you and depending on the problem. Okay, because it's like if you know about random forest, you know there's something called the number of trees. Okay, so meaning like the more trees you have, the better your model performs. Until it gets to a certain point, it starts overfitting. Okay, so the layers is similar to that. So the more layers you have, the more complex your model becomes, but it gets to a certain stage, it starts overfitting your data. So if you have small data, just like the case of this breast cancer that we have just, I think, about 600 points, it's better to use a small layer or a small neural network, probably 2 layers and the rest. Okay, so it depends on you. Another question is, can you expatiate on the number of outliers that should be used? Now, I said for binary tasks, you can use a single node at the output. You can use a single node at the output because the single node is predicting probabilities, and you can interpret probabilities as one of 2 classes. Excuse me. Let me go drink some water. Okay. But if you are trying to for example, if you are trying to predict binary classification, which is 2 classes, you can use a single node, like I said. If you are trying to predict say 3 classes, you can use 3 nodes. 4 classes, 4 nodes are the output. And how do you know? Okay, I think I've explained that. All right, so let's move on. Okay, so I was talking about the weighted sum. So we can actually use the matrix. So X, we hold all the features, W, we hold all the weights, and B, we hold the bias. And the bias is going to be just 1. So we're going to have 1 bias going into this guy. Okay, so that is the idea. So now, meaning we are going to have each weight vector, which is this guy, for each of the node. So meaning this guy is going to have his own weight vector, this is going to have his own, this is going to have his own, and this is going to have his own. So computing these things individually is going to be difficult. So that is why the idea of matrix multiplication came. So you can actually stack all the weights together into a matrix, then stack all the S values into a matrix, then you can do the weighted average at once instead of doing them individually. Okay, no more questions there. Alright, so let's talk about the weights and bias. Now remember when I told you that neural network simply tries to predict, tries to get these weights, because if it can get the weight, it can actually make prediction. So the overall goal of a neural network is to get the correct weights of each of the feature. So how does the first feature affect my prediction? How does the second feature affects prediction? So it's trying to get these individual weights and that bias term. Okay, so meaning we have to first start the neural network by initializing our weights at random. So once you initialize the weight at random, once the training starts, the neural network actually checks the prediction, make a prediction, calculates the loss, takes it back, and updates each of these weights. Okay, so the weights and biases are the learnable parameters. These are the most important parameters in your neural network. If you can get the right weight and bias from a problem, you can actually make predictions anywhere at any time. So the overall goal of a neural network is to get the optimal weight. That is why it's called training. It is training because it wants to get the optimal weight. If you look at this animation over here, where we have a neural network trying to predict a class of numbers. So you can see for 0 to 9, you can see we have 10 output nodes, one for each class. That's why I told you that the number of output node depends on the number of classes you are going to predict. Okay, so you can see it takes the input, which is this guy. This is just a matrix, 28 by 28 matrix. You stretch it out, you have 784. So you pass it to this node. You can see the input node, which is this, is going to be 784 node, one node for each feature. Okay, so it passes it into this guy. You can these green things you can see here, they are the weights. So it's passing the weights. So it's going to be making calculations, weighted average, and passing them to each of these. And at the end, it makes a prediction. This is an already trained network with weights already. That's why the weights will tell you which of these nodes is going to be activated. Okay, so if the weight is high, you can see this node is going to be activated, this, and this for that particular class. So the weight corresponds to what you are trying to predict. I don't know if you can get it that way. Okay. Somebody is asking, what if our target variable is continuous? What's the preferred number of feeding and output? Yeah. Okay, if your target node is continuous, then you use just a single node. Now that single node is not going to be predicting probability, it's going to be predicting continuous feature. So there's a particular type of activation you are going to use. Okay, like for this guy, for a binary classification, in this output node, the activation is going to be using is called sigmoid function. The sigmoid function can take your predictions and structure it into a range of between 0 and 1, like probabilities. But if you are going to be predicting for regression tasks, you are not going to be using a sigmoid function in this part of it. Okay, so you are going to be using different types of function, another type of activation. Okay, sorry, so you are not going to be using an activation function if you are predicting a regression problem. How do you know when you are overfitting? We'll get to that. Okay, so let's quickly move. So this is an example of a network. So the weights and biases are like the most important thing in a neural network. So we'll start the network by initializing the weights and bias. Then from there, the network starts learning and updating the weights by itself. Okay. So we're going to be writing some code now. So now this is our network we are going to be building. Remember, so this is going to be the input layer. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 input feature. Input node. Why? Because we have 9 features in our data sets. Okay, so please take notes. If you have 10 features, your input is going to be 10. Okay, so we have 9 here. So we're going to start with 2 nodes in the hidden layer, just 2 nodes. So you can see each of the 9 features is going to go into each of these nodes. Then we're going to have 1 node for our output layer because we're predicting a binary class. Okay, so this is the network we're going to be building at first. Okay, so the first thing we have to do is to initialize the weights and the biases of this network. Okay, then we can move on to the other stuff. Okay, so I'm quickly going to okay. So now how do we initialize our weight? I said we're going to be initializing our weights randomly. So randomly means that we can draw any number from a random distribution. Okay, so let's look at this again. If we have 1, 2, 9 input features and we have 2 nodes, remember I told you that each of these nodes carries its own weight and its own bias. This is going to have its own weight and its own bias. So meaning we are going to have 2 weights in this space. We're going to have weight 1 and weight 2. Then we're going to have bias 1 and bias 2 for this hidden layer. Okay, then for this final layer we're just going to have 1 weight. Okay, so this is going to bring 1 weight. Then we're going to have 1 bias. So please take note. So in this part, sorry, let me take that again. In this part, we are going to have 1 weight for this hidden layer. Then we're going to have another weight for this output layer. They are going to have one bias for this hidden layer, one bias for this output layer. So imagine if you are going to be having a network like this with 3 hidden layers, meaning you are going to have a weight matrix for this layer, another weight matrix for this layer, and another weight matrix for the last layer. So you're going to be having 1, 2, and 3 weight matrices. You're going to be having one bias for this layer, another bias for this layer, and another bias for this layer. So you're going to be having 3 bias. So but in our case, since we have just a 2 layer, which is this and this, remember I said we don't count the output layer, so we're going to having just 2 weight matrices, W1 for this first layer, W2 for the second layer, bias 1 for this first layer, and bias 1 for the second layer. So let's initialize that. So so what I'm going to do is going to be creating I'm just going to create some variables first. Layers. Now remember our layers is 9. Input is what? 9. Let's see, 9 here, 2 here, and 1 here. Okay, so 9, 2, and 1. So that's our layers. Then I'm going to create a variable called param. Parameter is going to be a dictionary. This dictionary is going to be holding all our temporary calculation, all our temporary weights and biases. It's just one node in the output layer for reversion. Okay, somebody's trying to answer that. Okay, no problem. Okay, so I'm going to create this guy, and I'm going to do something. I'm going to set a random seed. A random seed will help us initialize the same weights and biases every time we run this cell. So I'm going to set a random seed to be to 2. So the idea of random seed is that anytime you call np.random, for example, I'm going to call np.random I think random random n. This is going to generate a random number from a normal distribution. So you can see I have this randomly. So if I run this guy again, you can see I have this. It's generating a random number. You can see I have this. Okay, but if I use I think there's another one called random int. Yeah, random int. It's going to be generating a random integer for takes one argument. How many? Okay, let's see, I'll go with 1. So you can see 0 at first. Let's run this again. Oh, 0 again. Oh, sorry, I have my random seed here. That's right. Let me use 3. Basically, I have the same thing. Oh, because I ran the seed already. Okay. But you get the idea. So we're going to be using this random n because we want to initialize our weights from a random distribution, a random normal distribution. Very important. Okay, so I can also specify the weight, the shape. So for example, I can start to create a 1/5 matrix object. Oh, okay, so you can see I'm creating a 1/5 matrix that each values is a random number. Okay, so if I can decide to use 2, for example. Yeah, so I have this. Okay, so that's what we'll be using for our weights. So for W1, I'm going to call it W1. So I'm going to be saving them inside the list. So W1 is going to generate a random number. Now, what is going to be the shape of W1? Now, remember, our input is 9, and the first init layer is 2. Okay, so if we come back to our slide, remember you have 9 input feature, 2 hidden layer, and each of these guy is going to be having its own weight. So this is going to be having weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, weight 7, weight 8, and weight 9. So we're going to be having 9 dimensional weights by 2 hidden layers, because each of this one is going to be going into 2 nodes. So our weight is going to be a 9, which is this, by 2-dimensional matrix. Okay, so if we come back here, we're going to be having, so you can see the first in the list and the second. So let's just make it standard. going to just subset list of 0, which is 9, by layers of 1. Okay, so that's our first parameter. So if let me just quickly show you this. Okay, so now you can see it's a 9 by 2 dimensional matrix, where each of these, for example, this first weight is for this guy going to this first one. Okay, then this second, which is the second dimension, is for that same guy. Is for this same guy, but now going to the second node. That is why it's a 9 by 2 dimensional matrix. Okay, I didn't see any question. Why are we having 2 nodes in the hidden layer? Okay, I said it depends on you. You can have maybe 5, you can have 9, you can have 10. It depends. So the more you have, the more complex your network becomes, because we are going to be using our hand. We're going to be hand calculating most of all these variables. I decided to make it just 2. We're supposed to make it 1, but I wanted to make it 2 so that we get the idea faster. Okay, so it can be any number. So now we have our weight 1. So meaning we have weight which is for this first layer. Now we're going to have the second weight. Now the second weight is going from year to year. So the second weight is going to be taking 2 inputs, which is 1 weight for this, 1 weight for this. So it's going to be 2 by 1. So the second weight, which is I'm going to copy this. So it's going to be, I think, 1 by the last, which is 2. So let me just quickly show you this. Okay, so you can see we have 2 by 1. So this first weight is for this one, or this guy going to this, and this second is for this guy going to this. Okay, so we've initialized our weights randomly. So the idea is that once the neural network learns, it's going to be updating these weights. Each phase of the learning is going to be updating these weights. So for example, we started at randomly at first, but after some training, the network is going to create its own weights. So meaning each of these nodes is going to be assigned their own weights. That weight is what the network will use to make predictions in the future. Okay, so please take note of that. So we're also going to initialize our bias. Now remember I told you that the bias is, we are just adding a single bias to each layer. So we're going to add 1 bias to this. We're going to add 1 bias to this. Okay, so for our bias, I'm going to call it, I'm going to also save it in B1. Okay, I'm just going to copy. I'm just going to copy this. Now, what's going to be the size of our bias? It's going to be 2, because it's going to be adding 1 to this, 1 to this. So it's going to be just 2 dimension. So not 2 dimension, 2 feature. So that's 0 and 1, 2. So 1 is okay. I'll remove this. Okay, so I'm going to copy this for the second B. Now for the second bias, which is 2, we are adding it to just 1. So it's going to be 1. So that's the last layer. So that's this layer, which is 2. Okay, so we have initialized our weights and bias. Now notice that we can also initialize these guys to 0 also. We can initialize the bias to 0 and even the weights to just 0, starting at 0. But people notice that there's a problem with initializing weight to 0. If you start at 0, there are some calculations your network is going to do. Maybe it's going to do some divisions and the rest. And if you start with 0, it's going to affect your network during training. So it's best to initialize with random values like this. Let me see if there's any question. Is there any library for neural network, or only NumPy will do? So the idea is that, of course, you have lots of libraries for neural network. You can't be writing this guy from scratch every time. So the idea behind this class is actually to do it from scratch so that you can better understand how it works. Okay, because there's TensorFlow, there's Keras, there's PyTorch that you can actually use and just call them, and you can get what you want. But we're going to be doing it from scratch by ourselves. Why? Because there are some things you're going to be learning on the way. Then somebody is saying, exactly my thoughts. Why? Okay, when the weight is randomly generated, won't it affect the performance of the method, especially when high weight is generated? Okay, the idea is that once you generate this weight it's just like a starting point. So once you generate a weight at first, the network makes a prediction. Maybe it's going to be very, very wrong at first. So once it makes the prediction and it sees that it's very, very wrong, it's going to start adjusting the weights. Maybe start coming backward, start decreasing it as time goes by. Okay, so sometimes you can randomly generate a weight and you are close to the true weight. So that's why it's called random. So it happens that way. So somebody said, can't we study the data to infer on possible weight? How do you propose to do that? Okay, maybe you can share with me. And somebody is saying random seed is just like, okay, it's answering a question. All right, so we are done with that. Okay, so we've initialized our weights. Now remember, I saved each of these weights into a dictionary so that we can easily access them later. So this is just going to be like a temporary storage location where we'll be keeping all our variables. So we initialize W1, W2, B1, and B2. And we also have our X. Okay, so we also have our X train. Sorry, I'm scratching my eye. There's no virus in this place. Okay, so basically, now let's go back to our slide. Okay, so we've initialized the weights. Okay, now what's next? Activation function. Now remember, we said the weight, which is this weight, is going to be multiplied, this matrix multiplication with the input, which is X. Then we add the bias. So in our network here, we already have our weights, we already have our bias, we already have our inputs. So basically we can do something like, we want to do something like the weight dots, which is matrix multiplication times, for example, say X train, then we want to add our B. Then this is the weighted average that we want to perform. Okay, so if we perform this, we are going to have to pass it through an activation function, like I said earlier. So you can see we have, the weight X, the bias. Once we perform this mathematical function, we pass it through an activation function. So there are lots of activation functions that you can use. Okay, so I think I did oh god, okay, yeah, this is it. So you can see each of these nodes will perform the weighted average, passes it through an activation function. So please take note of that. So where was I? Activation function. So there are, like I said earlier, there are different types of activation functions that you can use. There's the sigmoid, there's tan h, there's ReLU, liquid ReLU, and the rest. So the meaning of these activation functions, they are just non-linear functions. They can take a value and they can transcend it into a particular range of values. So they perform non-linear functions to your data. Okay. So if you take this is a linear function. If you take this function and pass it into an activation function, it becomes non-linear. Okay, so we have sigmoid, we have tan h, ReLU. So this is like the most popular activation function for hidden layers. Okay, the ReLU function, and it's a very simple function. It just compares each value in your calculation, each value with 0. If the value is less than 0, it will replace that value with 0. And if the value is greater than 0, it will keep that value. So it's just like removing negative values and keeping just positive values. Okay, so let me quickly, maybe I should just show you something like that. So for example, I have this array. Okay, so I'm going to use params w1. So this is my function. Now you can see there are some values that are greater than 0 and there are some that are less than 0. If I pass this through a ReLU function, ReLU is very simple. So ReLU is just simply np dot max 0 and only integers, scalars. What am I doing? Okay, wait. I think only integer scalars can be converted to scalar index. That's weird. Okay, maybe I should use the maximum function. Okay. Good. Oh, it's the maximum function. Okay, so np.maximum 0. Now remember, this is a matrix. That's why I'm using the np.maximum, not just maximum. Yeah. Okay. So you can see values that are greater than 0 are kept. Values that are less than 0 are removed. So you can see this minus 0.47 is replaced with 0. So this is your ReLU function. Okay. So that's the function of a ReLU. Then you have sigmoid. So the ReLU is very, very popular. So we are going to be using ReLU as an activation function for each of the hidden layer. Then also another important function is the sigmoid. Okay. So the sigmoid, this is the ReLU. Okay, I was talking about. So you have 0 if x is less than 0, x if it is greater than 0. So it's also called the rectified linear unit, and it compares the value with 0 and that puts the value if it is greater than 0 or otherwise. So if you plot it, it comes out something like this. Let's see, can we plot this? 2 dimension. Okay, let's do it. Then the next one is the sigmoid function. The sigmoid function is very popular also, and it's mostly used for the output layer. It can be used for the hidden layers, but it has been shown with practice that the ReLU function actually performs better than the sigmoid function, and it's also easy to calculate than the sigmoid function. So we prefer to use the ReLU function for the hidden layers. Then if you are going to be calculating or predicting a binary class, you can use the sigmoid function for the output layer. Why? Because the sigmoid function can take real values and convert them into probabilities, into a values between 0 and 1. Okay, that's what the sigmoid function does. So the sigmoid function is simply 1 all over 1 plus the exponential of the value. So for example, a simple sigmoid function, we are going to be writing a sigmoid function. Okay, so I believe we should just write it. Okay, I think we should just write it. Yeah, let me see. Yeah, cool. So we are going to be writing the sigmoid and the ReLU function because we are going to be using it. So it's a very simple function. This is for the ReLU. So something like I'm just going to create a quick function called ReLU. ReLU takes, for example, Z. It's mostly called Z. Why? Because we have, Z is the calculation. So after calculating, you pass it to the activation function. Okay. So I'm going to call Z. So it's just going to return this guy, np.maximum, but instead of this, it is going to return the parameter passed to it. So that's Z. So that's really very simple. Then let's also define sigmoid. Sigmoid is also going to take the function, and the formula for sigmoid is 1 all over 1 plus the exponential of minus x. So if we are going to code this, we are going to be return 1. I'm using 1.0 because I want to return float values, not integer values. So 1 divided by 1.0 plus, I'm going to use, remember we're using numpy. This is the exponential function in numpy of minus the z, okay, which is this guy, 1 divided by 1 plus exponential of minus x. So that's this. So if you take a look at the sigmoid function, for example, let's try using the sigmoid function on, I'm going to run this cell first. Let's use the sigmoid function on, say, param W and C. So normally this is the parameter of W, okay? So let's use it here. Sorry. Sigmoid of this guy and see. Okay, no question yet. Okay, so now you can see it has taken these values and it has squashed them to between 0 and 1. For example, most of them are between 0 and 1 actually. Like, but this one is more than 1, so 1.0. So I think we should use, let's use maybe big values. I'm just going to create a simple temporary array, TMP. I just want to show you how sigmoid squashes value. So let's just say 200, 20, 30, 1, 37, for example. So if you pass this TMP into a sigmoid function, it's going to squash it to a value between 0 and 1. So you can see. Are you seeing this now? So it's going to squash everything between 0 and 1. So that's the function of a sigmoid. So and the sigmoid function is mostly used, like I told you, you can use it for the hidden layers as the activation function for the hidden layers, but the ReLU is very popular for that. Okay, and it's very good, useful for that. So the sigmoid function is mostly used for the output layer when you are trying to predict probability. Okay, so these are other types of activation function you can look at. This is just a modification of ReLU. This is also a modification of ReLU. TANH is also very popular, but these are the two we are going to be using. So we've written the code for that. So we've done the first part, initialized the layer of the network. We've initialized the weights. We've written our activation functions. So I'm just going to add activation functions here. Okay, so let's move on to the loss function. Now, the idea behind remember I told you that the idea behind neural networks is simply to train those weights. Okay, so if you have the weights, okay, you guys can't see the board, so I'm just going to explain. If you have 3 weights, for example, and you want to update those weights to make predictions. So how do you know if your network is doing well? How do you know if your network is performing well? So you can only know if you make a prediction at first and compare that prediction with your targets that you have. Okay, so if you have a target that is say 1, and you make a prediction of say 0.2, how do you know how far your network is? So that is the idea behind the loss function. So the loss function actually tells you how far your network is from the true value. So it measures how good your model is. So if your model is bad, you can get an idea from the loss function. Then you can know, okay, maybe I should increase the weight. So if you increase the weight and you make a prediction again and you calculate your loss is higher, you can say, okay, I should still decrease or increase the weight. So the loss function kind of tells you how to measure how good your model is. So I say, please, can you force save so the notebook will update for us to see it? Oh, can't you guys see it? Okay, so I don't know, overwriting the last save from the file menu. So probably I'm going to save it. Would you like to overwrite existing changes? Yes, I want to overwrite it. Okay, so I believe you can see it now. Alright, so we have, actually I was talking about the loss function, okay? So the loss function is a way of measuring how good your model is so that it can adjust the weights and biases, okay? So you have different types of loss function. I'm going to come back here. Okay, yeah. Now, what exactly is happening here is that once the network makes a prediction, okay, this is already a trained network, so I'm going to use this. So once it has initialized random weights at first, for example, calculates the weighted average, pass it through an activation function, probably ReLU, passes it here. For example, we're going to use a sigmoid function at this last layer, makes a prediction. So if it makes that prediction, The loss function will tell you how far that prediction is from the true value. So you calculate the loss here, then you know how to change your weights and biases. Okay, so that's the idea behind the loss function. And your loss function will actually depends on the type of task you are working on. Okay, if you are working on a regression task, you can use something called the mean absolute error. You can use mean squared error. But if you are working with classification problem, there are different types of losses that you can use. And the most popular one is called the cross entropy loss. But the cross entropy loss is from information theory. It actually measures the difference between two distributions. So this is the formula for the cross entropy loss. So this is the loss that is most popularly used in classification tasks like ours. Okay, so and this is like the general formula for classification problem. So it actually depends on the number of classes you are trying to predict. So in our case, where we are trying to predict two classes, which is if somebody has benign cancer or malignant cancer, we are going to be using the binary cross entropy, which is this. And there's a way you can get this binary cross entropy if you expand this function by replacing the number of classes with 2. If I replace the number of classes with 2 here, which is 2 classes, and expand, you are going to come out with this. I'm not going to be doing that expansion because of maybe, but it's very easy. So just put a 2 here, then expand this, because this is the sum. This is like a summation. So you sum this and add it. So if you are going to be working with 3 classes, for example, you are going to having 3 here. So you can bring out your function. Okay, so this is like binary cross entropy, and is what we are going to be using to calculate our loss. So you can see we have y and y hat. So y is the true prediction, y hat is the prediction we make. Okay, so if you put in your y and y hat into this binary cross entropy, the value you are going to be deriving from this is going to be called your loss. So it shows you how far your predicted value, which is y hat, is from your true value. Okay, so we're going to put this in code. This is going to be our loss function. Okay, so let's write that. It's a kind of long function to write, so I'm probably going to sorry about that. So let's call it I'm going to call it binary cross entropy. Thanks, we can see it now. Okay, somebody is asking what's really doing, since it's comparing variable with 0 and picking the maximum. Okay, so that is kind of like a non-linearity, because it's telling you that if these values are less than 0, don't use them, don't activate them, because it draws similarity with what happens in a human brain. Because sometimes scientists have shown that if you see an image, for example, of somebody you recognize or somebody you know, there are particular neurons in your brain that actually fires or becomes active to tell you that, okay, I recognize this person, I don't recognize this person. There are some particular neurons that will become activated. So the relay is telling you that some of these weights don't need to be activated. They should be brought down to 0. They are irrelevant. So it's kind of giving you like a non-linear function. Instead of just passing all the weights directly, it's going to remove some from it, make it non-linear. So that's what the relay is really doing. Okay, so we are going to be writing the binary cross entropy, and so you can look at the, let me see if I can expand this so that we can write it out. Okay. Sorry, I'm trying to, write out the, alright, so I can be looking at the formula and convert it into code. Okay, so for the binary cross entropy, we are going to be having minus, let's see, sorry for the delay. Okay, so I'm looking at the formula. So we have cost entropy between, so we're going to be having between y, which is your true value, and let's call it y at, which is your predicted value. Okay, so how do you calculate this? So let's see, okay, let's call this loss. So the loss is going to be minus, now if you look at the this, we have minus y of I log of y at. Okay, so let's write this part of it first, but I think we can make it simpler. If you take this minus sign and you expand everything here, you are going to be having, here will become positive and this will become plus. Okay, so I think that will be better. So we can write this separately, and then write this separately. But let's start with this first part. If we have this first part, we have minus yi log y at. So I'm going to put this in his own brackets. So minus y. Remember, we're using let's use numpy. We're going to be using numpy because we are working with matrices. So if we're going to be using numpy, this is multiplication. Okay, so let's use np dot multiply. What are you multiplying together? Minus y, where's y? Comma, no, we can't do minus y, so probably put it out here. No, let's see, let's make this thing simpler. Minus log, okay, maybe instead of switching back and front, I should just write it out here. Minus y log, I think call this y at, something like this. Oh, so that we can look at it together. 1 minus y log 1 minus y at, okay? 1 minus y log of 1 minus y at. Yeah, that's it. Okay, so this is the cost entropy. So now I want to convert this guy to code. Okay, so this minus sign, we can multiply through, and this can give us, I'm trying to make this as simple as possible. So we can multiply through this minus, and this can give us plus over here. Okay, so we can write this part first, which is going to be, we are multiplying y with log of y at. So np dot multiply y with np dot log of let's see, y at, yeah. So we have this first part, which is this, okay, then plus 1 minus y. Okay, we are multiplying this together, so np dot multiply this guy and log of 1 minus y at, which is np dot log of 1 minus y at. Yeah, I believe that's it. Okay, yeah, that looks like it. This y np dot log y at np dot this np dot that. Can we okay, great. So we have our loss. Okay, so let's just return loss. Okay, let me see from the slide. Okay, so now let's test this binary cost entropy. So assuming we have, let's say I have my y to be np dot use 1 0 0 0 for example. So this is my true values, for example, and for example, maybe I made a prediction of, say, maybe after training my network, I have a prediction. I predicted 0 for the first class, predicted 0 for the second class, predicted 1 for the third, predicted 1 for the third, and 1 for the fourth. 1 2 3 4 5. 1 2 3 4 2 3 4 5. Okay. So assuming I have something like this, now how do I know? What's that? Oh, sorry about that. Collab, stop giving me autocomplete. We are missing the factorized minus. It's from the formula. Okay, factorized minus. Let's see. Plus, no, it's there. Remember, this minus is like whale is outside like this. Okay, wait, let's see. Yeah, it's outside. So if you use this, if you multiply through by minus, for example, if you multiply through by minus, it's going to cancel out this guy. Minus times minus will give you plus, so this guy remains the same. Then minus times this guy will give you plus this. So I think, yeah, that's okay. I think it should return negative loss. No, is not supposed to return a negative loss. The loss is not supposed to be, it can be negative, but it's not compulsory that it must be negative. But let's try this. Okay, so we have y and y prediction. Okay, so let's see if our loss function actually works. So we have binary cost entropy y and y pred. Okay. Aha. Divide by 0 accounted in log. So we have negative infinity, none. So that divide by 0 issue I was telling you about, if you initialize your this thing randomly, I think that's the problem here. So most of the time you are going to be having predicted probabilities, not constant values like this. So for example, I might have 0.1 for this, 0. Say something very small and close to. So I'm predicting probabilities instead of the actual values. 0.9, and this is 0.9. You know, if you round up these values, they still go to 1, but they are interpreted as probabilities and not actual values. So let's do this again. Okay, so you can see this is the loss. So meaning it's telling you that the cost entropy loss between the first prediction 1 and 0 is minus this. So you can see it's very low. So then look at 0 and 1, the same thing, also very low. Now let's look at 1 and this guy, the same thing. So it's calculating the loss for you. But now let's try to make them close to, let me see, let me give this one 0 0 0 0 1, something very close to 0. 2, for example. And let's look at the cost entropy. You can see it's getting smaller and smaller and smaller, as you can see. So meaning the closer we get, the smaller the loss becomes. Okay, so this cost entropy is actually doing a great job for us. Okay, but the issue here is that we want a single we want to calculate the loss relating to every how will I put this, relating to every point. Okay, so we don't want to return an array of the individual loss. We want just a single loss value, just one value that represents everything. Okay, so to do that, we are simply going to divide by the number of elements in this. So we want the average loss, not just the single loss. Okay, so we are going to divide by let me see, then we would have negative. Okay, it's from the formula. Can we help you? Okay, I think we're all good. So I'm going to simply divide by the sample, let's see, no, by the length of y. So it's like we're taking the average. So let me see, minus this. Okay, all good. Okay, so if I run this again, run this. Okay. Oh, it's dividing each. Sorry. I'm supposed to have a single. Wait, let me see. Here's my loss function. Okay. Oh, this actually works. Okay, so this actually works. So we'll fix the average loss later. For now, we can work with just these individual losses. Okay, so let's work with this. So our loss is okay. Our loss works. Let's see. Okay, so we have this. So let's move on to the next one. We've done that within some code. Now, okay, so I think we have almost everything that we need to do our forward propagation. I'm going to explain that in a bit. Let me just clear this. Okay. Yeah. No questions yet. Okay, so we have what we've done so far. We've initialized our layers. We've initialized our weights and bias. We created our ReLU function, our sigmoid function, created our loss function. I'm still a bit skeptic, but I think I'm missing something in this loss. But let's move on. Okay, so we have our loss function. So meaning we can calculate our weights, pass it through activations, calculate the loss, and that is the forward propagation, which we are going to be looking at. So the forward propagation is just a series of computation performed by a neural network before a prediction is made. That it starts from the input layer, which is this layer, next to the hidden layers, perform the calculations, and to the final layer. Then once it gets to the final layer, it makes a prediction. And after that prediction, the loss is now being calculated. So what is the calculation that we are going to be doing? This is the calculation for the two-layer neural network. This loss has really lost. Please, where are we again? Okay. So I think you understand from the forward propagation. Just look at the forward propagation. You better understand the loss. What we are going to be doing is that first, in this first node, in this first layer, which is this guy, we have our weights and we have our biases. So we'll do a weighted average, which is x times the weights, which is weight 1, plus the bias from the first layer. So from this first layer, we do our weights times our inputs, okay? Then we add our bias, which is this guy, okay? Then we pass that result into an activation function, which is called ReLU. We are using ReLU, okay? So we save that result into what I call A1, which is activation 1, okay? Then we take this result and pass it to the next node, which is, we take the result from here that has gone through its activation and pass it to this next node. So this next node, which is the final node, is also going to do its own weighted average with the results from this second layer. So we take the A1, which is this A1, times the second weight plus the second bias, save it into Z2. Then we perform now instead of using another activation function like ReLU again for this, we are going to, because this is our final layer, we are going to be using the sigmoid activation function. Why? Because we want to predict probabilities. If, for example, we had another hidden layer here again, we can decide to pass the result from here to that hidden layer. That hidden layer also does its own weighted average, passes it through its own activation function, which can also be ReLU again. Then when it is done, it can pass the results to this final layer, which is also going to do its own weighted average an addition of the bias, but this time we're going to be using a sigmoid and not the ReLU, and that sigmoid of that activation of that function is going to be saved in what is called y-hat. So y-hat is like our prediction that the network has made. So meaning the network, let's go back again. The network, this is the input x, so we'll perform a weighted average of x and the first weight plus the first bias, which is for the first layer, which is this layer. Then we'll take that calculation and pass it through an activation function, and we'll decide to use what? ReLU for it. So the result is now going to be sent to the second and final layer. So that layer also does its own weighted average with weight 2 and bias 2, saved it into Z2, and passes that Z2 into a sigmoid function because we want probabilities, and it's going to save it in y-hat. Now when we are done with that, this y-hat becomes the prediction of the network. So we take this prediction and pass it through our entropy function. So the entropy will now calculate the loss between this y-hat and the true values. So the network now knows that, okay, so this is my loss, this is how far I am from the correct values. So it's going to now go back and adjust the weights through a process called backpropagation, which we are going to be doing in the next session. Okay, but for now we have to put this into code. Okay, do this calculation, calculate the loss. Okay, so that's the next part. So let's write the code for the forward propagation. Okay, so I'm going to quickly call this the forward propagation. Okay, no question yet, so probably just going to take a quick short break. And so guys, give me a minute. I'm going to take a quick short break, and this is the bathroom. Okay. So sorry for the delay, guys. So let's quickly go back to this. Okay, so we are talking about the forward propagation. Okay, so all right, so I believe we all know what we're going to be doing. So we have Z1, XW1, B1, and the rest, and we have this guy. Okay, so the first thing we're going to be doing is calculate for Z1, which is for the first layer. Okay, so probably, let's see, Z1 is equals to the dot product between X and W1 plus B1. So what is X? X is this guy, X train. Okay, so I don't like the name X train, so I'm just going to call it maybe okay, I'm going to call it X in, for example. I don't like the name X train. Okay, and I'm going to call it, I'm supposed to use X, but I already used X here, so I don't know. Okay, I think maybe I can change it here. Variable names are a thing of pain. X in, and so I'm just going to run this guy again. Okay, so I don't want to use the X train directly. Let's see, concurrent viewers. Okay, yeah, good. Okay, so I'm going to assign this X and Y is equals to Y train. Okay, so now we do our dot product. Now remember, the dot product is between X and Y. Okay, so let's see, we do X. You can do, since these are all matrices, they are in matrix format, array format, so you can do X dot W, which is this guy. Please take note. Let me go back to the slide again. X dot this plus B in Z1. Okay, so Z1 is going to be X dot plus B1. Okay, so that will be our X. Then we also calculate the value, passing this into this and give it a. So let me see if this works first. I should probably put this in its own cell. Okay, so I'll just look at the results of Z1. Alright, so this is the dot product. Okay, so copy this. No need to copy this. So A1 will be the value. Now I've already written our function for value, so we'll just call value and we'll pass in the results from the first calculation, which is A1. Okay, so we are done with this and this. Now move on to the second layer. So Z2 will be the results from this dot product with W2 and B2. So I'm just going to copy this guy. So Z2, remember, if you have any question, you can always use the live chat session. So this will be A1 dot W2 plus this guy. Then the last one, which is Y art, we're going to pass it through a sigmoid function, and that will be the prediction. So Y art will be equals to sigmoid of Z2. Okay, so let's see if this works fine. Oh, works fine. Wow, amazing. So this is Z2. So I want to look at the predictions the network made. So you can see these are all the predictions the network made. At first, why? Because remember we initialized the weight at random. So these are the predictions it made. So I'm going to round this up. Round this up to, round this up to 1 decimal place. Or let me just use round. Then show the first 6, for example. So it predicted 0, 0, 0, 0 or true. 1 decimal place. Oh, it's already in 1 decimal place. Sorry about that. Okay, so now let's look at our true values, which is y to 6. So you can see we have a mixture of 0, we have 1, and this guy is just predicting 0. Why? Because we just initialized the random weights and just made just one forward pass. This is called a forward propagation. So we just made forward pass by just once. So you can't, the network can't actually perform well because these weights and biases were initialized randomly. Okay, so you get the idea. So the forward pass just performs this on the first layer. So this, everything happening here is from this first, is for this first layer. Okay, so after doing that, we pass the results to this guy, to the second layer, then we'll make the prediction here. So after making this prediction, we will have to calculate the loss. So the loss becomes, call our binary cost entropy, pass in y, is it y? Let's see, y first, okay. Y, which is the true value, and y hat, which is this our predicted values. So we can see how far the predictions are from the true value. So if I calculate, if I look at the loss, so you can see each of the predictions, it's telling you how far they are from the true value. This is our loss function. So using this loss function, how can we update the weights and the biases? That is the question. That is the job, the whole job of a neural network. Okay, you now know how far you are from the predicted value, from the true values. So how can you change your weights and your biases so that your loss, your overall loss will decrease? I think your loss has to be a single value. Let me see. If I divide, I'm going to quickly check something. Yeah. Oh, that's the problem. I'm supposed to sum this. Let me see. Yeah, I'm supposed to sum this. So I'm supposed to sum this together. Yes. So I'm just going to add it. I'm supposed to sum this because we want a single value for the loss. Not that was what I was saying earlier, not the whole array. So we want just a single value for the loss. So I'm going to sum this and divide by this number. So we want an average. So dividing by the length. Oh, sorry. So it's like we're taking the average loss of everything here, not just a single loss. So we want just a single value that we can use to say, okay, this is the single value across all the weights. So this is the direction you are supposed to go to. So that's why we want a single value. So my bad. So we use the sum function there. Okay, no questions yet. No questions yet. Okay. Meaning you are all following. So let's look at the single value for the loss now. Oh, still not single. What's happening? Did I sum this right? Oh. It's supposed to be this. I'm making some silly mistakes. This is supposed to be an overall sum. So I'm quickly going to rectify this. This guy, okay, this for this for this. So I'll probably just take it back. Okay, so instead of using this plus here, I'm going to put this for this, this for this. Let's see, this for this. Okay, so I'm going to put this. Sorry about that. np.sum. Yeah, and put a comma there. Divide by the length. Okay, instead of me to divide, I'm coming. Let me quickly check. Okay, I'm going to quickly confirm something. Oh, okay, multiply. Alright. So let me run that and check this again. Okay, I think I'm just going to quickly bring, I have it here. So this is the part. Oh, okay. So the idea is to, if we are taking the average, we sum this part, we add this part to this part, we take a sum of everything, which is np.sum, then we divide by this number of samples, we multiply by the number of samples, which is also the same thing as dividing by the number of samples. Okay, I think, so this was a negative sign. I think somebody was talking about that negative sign. Yeah, let me see. Yeah, I think Sadiq was talking about the negative sign. Yeah, so basically we want the average, so we take the sum of everything here and we multiply by the number of the sample, becomes the length, which is the number of the length of y. Okay, so I think this should work. So let's run this again. Y hat is not defined. Oh, I'm using sorry about that. This is small letter, not capital letter. Okay. Live coding. It always messes you up. Okay, so we got that now, a single value for our loss. Now this is just telling you, giving you one-time warning that there might be some division by 0 that you will encounter. Yeah, and it happens because of the way our weights are initialized. They're initialized randomly, so some values are actually close to 0 or 0, so that's why it's giving you this warning. Okay, so alright, so we have that. So basically the idea here is that we convert this into code. Now we are not just concerned about each of the losses, we are concerned about a single loss that we can use. So that's why we are summing everything together and then multiplying by the number of samples. That's like taking the average loss. So the average loss becomes this for the all data points. Okay, so we have that. All right, so that's for the forward propagation. So we've done this, move from here to here to the loss. Now we've gotten the loss. Now how do we use this value? We know that our loss is 4.54, and the best loss to have is actually 0. So once your loss is 0, you know that your model has learned correctly and the weights and the biases have been fully updated. Okay, so but how do we get from 4.5 down to 0? Okay, so that's the idea behind backpropagation, which we are going to be seeing. So the idea is to use this loss function to update your weight in such a way that this loss actually reduces, it goes down. Okay, so that is the idea behind backpropagation. So during the training phases, you go through the front propagation where you calculate your weighted average, activation function, make a prediction, calculate the loss. Now once you get that loss, it takes it back using that loss, using the system or the algorithm called backpropagation, which I'm going to explain shortly, to update each of those weights and biases. Okay, still no questions yet. Okay. So backpropagation is simply a backward propagation of error. It's an algorithm or a supervised it's an algorithm for supervised learning of artificial neural network using gradient descent. Okay, so the idea is that now we have the loss. Now, so there's something beautiful about mathematics that we can actually use to calculate how to change the weights with regards to the loss, and that is called calculus. Okay, so calculus can tell you how the change in a particular term affects another particular variable. That's just simply calculus for you. So if you know the speed, if you know how the speed is changing, you can get the velocity, something like that in physics. So it calculates the change with respect to the other variable. So if we know the loss of our function, can we use backpropagation, which is using calculus, to calculate the how to change this loss, or in what direction to change these weights and biases that it will decrease this loss? That is the idea behind using calculus in backpropagation. Okay, so we can calculate something called the derivatives, whereby we can calculate the derivatives of the loss with respect to the the weights and the biases. So if we can calculate the derivative, we know in what direction to change our weights that will make our loss to decrease. But for you to calculate the derivative between two variables, they must be related, meaning they must have, meaning as you are changing one, it's affecting the other one. But the problem here is that we have lots of functions that were computed before we got to the loss. Okay, so for you to get to the loss, you computed z1, a1, z2, y hat, but you want to change w1. Now in this part, you don't directly have access to w1. So for you to be able to change w1, you have to look at the intermediate calculations that have been done before. So it's like you are walking backwards. So you can calculate the derivative of the loss with respect to the output, which is y hat, because we have this one currently. So you calculate the derivative of this with respect to this. Once you have that derivative, you keep it. Now you calculate, how did you get y hat? You calculated sigmoid of z2. So you calculate the derivative of y hat of z2 with respect to this guy. Okay, so once you calculate that derivative, you add it or you multiply it with the one you calculated here. So as if you are taking it and adding them backwards. It's called chain rule in calculus, whereby you can calculate intermediate derivatives and add them together by multiplying them. You chain them together. Okay, so meaning you calculate at first the derivative of the loss with respect to y hat. From there you move to this one, the loss with respect to this guy. From there you move to this guy. Now you can see we have w2 in this stage. So those intermediate derivatives, we keep adding them and adding them and adding them together until we get to our weights and biases. Once we get here, we can move backwards again, calculate the derivative of the loss with respect to this. From there, we'll move backwards till we get to the final layer. That is why it's called back propagation. So you are going from the end, which is the loss, calculating the derivatives and chaining them together using chain rule till you get to the final or the first weights and biases. Okay, so now how do you calculate these derivatives? It's actually mathematically intensive, but most of them have been calculated and you can easily just take the formula and use them. Okay, so for example, how do you calculate the loss, derivative of the loss with respect to the output, which is y hat, which is the entropy loss? And remember, the entropy loss is this guy. this long guy over here. So you are trying to calculate the derivative of this guy. Okay, so the board is not going to be clear. I wanted to do some of the derivatives for you, but the board is not going to be too clear for you guys, so I think we're just going to go over this. And there's also a very good tutorial on the derivatives. Yeah, it's a good Medium post by Patrick David that you can helps you understand. Okay, this is getting slow. Helps you understand that. I'm going to also add it. Yeah, I added it to the slide here, so you can click on this link and you can check. But I'm going to try and explain this as simple as possible. Okay, so the derivative of the loss with respect to the cross entropy of y hat. This is a derivative. Okay, so I call it the loss with respect to y hat. So if you put this in code, this is going to be the derivative of the last layer. Okay, so we have this guy, so we keep it somewhere. Now we move on to the next one, which is y hat. How did you get y hat? You calculated sigmoid of z2. Sigmoid is a function on its own, z2 is another function on its own. Okay, so now the derivative of the loss with respect to y hat. Now you can see we have dl with respect to y hat from the previous slide, which is this guy. You can see we are chaining it together with the derivative of this function. So we are taking the derivative at each step and pushing it backward. Okay, so now how do you calculate the derivative of a sigmoid function? It's very simple. The derivative of a sigmoid function is simply the sigmoid of the value times 1 minus the sigmoid of that value. All the derivatives are in this link. I don't know why this guy is not doing it. Okay, but you can actually click on it and follow. Okay, so that is for the second part. So you can see I keep calling them dl underscore wrt. So we have the loss with respect to z2. Okay, it's for this guy. So we chain the previous derivative times this derivative, which is simply this guy over here. Okay, then we'll move backward again to the next one. So how do you calculate the loss with respect to a1, w2 and b2? So you can see we have 3 different variables, so we have to calculate the loss for each of them. Okay, so the loss with respect to a1 is simply w2 times this previous derivative, which is this guy. So we can see we are still chaining, we are still adding them together. Okay, and the loss with respect to w2, which is this, is just a1 times drz2. Then the loss with respect to b2 is just this guy on his own. Okay, no questions yet. Okay, so we can move on. So take note, calculate the first loss, save it in this variable. So this is the derivative, so we're going to put it in code. We move to the next one. We chain the previous derivative, which is this, and this current derivative of a sigmoid, which is simply this. Okay, then we move to this third one, where we calculate the individual derivatives of each of these variables with respect to this loss function. So we have this, and from there we move to this, which is simply a value. Derivative of value is very simple. It simply returns 0 if the value is less than 0, and returns 1 if the value is greater than 0. So you can see the derivative of a value function is very simple, and that is one of the reasons why it is used as an hidden layer. Okay, because to calculate the derivative is very simple. Now, because the idea behind most of these hidden layers is that you have to make sure they are continuous and they are differentiable. Differentiable in the sense that you can calculate their derivative and use that to update your weights. So if, for example, we pick an activation function that is not differentiable, we can't actually do backpropagation. So that's one of the reasons why we use most of these linear functions. You can see the derivative of value is very easy to compute, just this. Okay, so now remember we are calculating a value of z1 with respect to this a1 and the loss as well. Okay, so we chain the previous value of a1 and this current derivative, so you can see, and this current derivative. All right, then move to the final layer, so which is having x w1 and b1, and it's similar to this. So here we have w1 becomes x times this, and b1 just becomes this. Okay, now remember we don't differentiate the inputs because we are not trying to change the input. Okay, so we only differentiate what we want to change. So we are trying to change it. So you can see we now have the loss with respect to the w1, we have the loss with respect to b1. Okay, we have the loss with respect to w2 and b2, and these are values that we want to update. Okay, so if we have the derivative, we can easily update. We now know which direction we can update the weights to. Okay, so you can see it's going from here backwards till we get to here. That's why it's called back propagation. And as it is going at each stage, it is taking that derivative that it has computed at that stage, taking it backwards and chaining them together. Okay, so most of these things are easy to compute. You can easily compute the derivative with hand. They are easy to compute. You just need to know basic knowledge of calculus and linear algebra. You can compute them by hand, but we will not just go into that today, so that we can quickly do this. So since we have all these derivatives computed, let's write the code for the back propagation. Okay, so I'm going to create a new cell. I'm supposed to turn off these warnings. I hate seeing warnings. So we have the back propagation algorithm. Okay, so remember the first part is okay, so we put this in code: minus y divided by y hat plus 1 minus y all over 1 minus y hat. So we call it the L with respect to y hat. Okay, so let's put that in code. So we call it the L with respect to y hat, which reads as the loss with respect to the y hat, is equals to, now minus, remember minus, all these are arrays, so remember to work with numpy. So we can say minus this divided by this, so we have minus of np dot divide y comma y hat. Okay, and remember we have y and y hat already. From here we have y hat and we have y. Okay, so np as y hat, then minus np dot divide of, let's look at the other one, 1 minus y and 1 minus y hat. So we have in brackets 1 minus y, outside in bracket 1 minus y hat. Okay, so that's the first derivative with respect to the y hat. Now the second one is let's look at the second. Okay, so the second one is the loss with respect to z2, which is this z2 here. So we have to calculate the loss with respect to the sigmoid, which is simply the sigmoid of y hat times 1 minus sigmoid of y hat times the previous answer that we got. Okay, so we have the loss with respect to, I'll call it z2. Let me call it z2. Yeah, that's what's there. So I'm going to put it in capital later. So it's simply this loss that we already have, we are chaining it together, so times, so instead of using times we can use okay, let's use times what's the other function, sigmoid, which is simply the sigmoid of y hat times 1 minus the sigmoid of y hat, which is just, no, not y, it's supposed to be z2, sorry, this is supposed to be sigmoid of z2 times 1 minus z2. This y hat times 1 minus y hat. Oh, this is supposed to be y hat times 1 minus y hat, not sigmoid. Sorry about that. So y hat into, or we can say, let me put this in its own bracket. So y hat times 1 minus, let's see, Okay, so this part is this part, so move the sigmoid. So we have to, let me just quickly run this and see. Invalid count encoder and chill divide. We're still having that issue of dividing by. I didn't set that seed. Random dot seed. Okay. Alright, so let's take a peek at the derivative. See, mostly negative, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, let's look at the loss with respect to y at the derivative. Okay, so let's keep moving. Alright, this is supposed to be done first. I'm sure that was why. So do this part before you do this part, and before you do acting here. So I think that was one of the reasons why we are having zeros. Good. Okay. Alright, so we've done that. Now let's move on to this part. Okay, so we're going to be having a loss with respect to a, w2, and also b2. Okay, and they are easy to compute. So we have the loss with respect to, I think the first one is, let me see, the first one is what? A1, yeah. So the loss with respect to A1 is equals to it's equals to rationing this guy. Remember, backpropagation, this comes here multiplied, this comes here multiplied by w2 times this. Okay, so let's see. What are you using to multiply? W2. So we're going to do a dot product. Now remember, W2 is saved in params. So this is what we're going to be using. Okay. So we have that. Let's see. What is the shape of? Now, when you are doing most of this multiplication, it's good to always know the shape of what you are computing, because if the shape don't align, your matrix multiplication is not going to work. So let's look at the shape. Your shape are not properly aligned. So let's see. Okay, so this is 559 by 1, this is 2 by 1. So if we are trying to multiply these together using, they are both matrices, if we try using dot products, I think that will give us an error, because we have, for two matrices to be multiplied together, the adjacent dimension, which is this and this, are supposed to be the same. Okay, so I'm supposed to have 1 and 2 here. Okay, so if I try doing this, I think I'm going to be having an error. Okay. Aha, I told you. Let's see. There's an error there. Oh, I'm doing. Can't multiply. See, shape must be this. So you can't multiply them together like that. So if I decide to use the dot product, yeah, I think I'm also going to have, yeah, dot shape do not match, so this and this together. So meaning I have to transpose the second one to be 1 by 2. So you can see that the adjacent dimensions are not aligned, so that if I multiply this together, I'm going to be having a 559 by 2 dimensional matrix. Okay, so meaning I have to transpose this guy. So please always notice and watch your shapes. Okay, I said that worked now. So I'm supposed to be having a 559 by 2 as my A. So let's look at the shape. Good, 559 by 2. So we have that. Okay, so we've done this. Now let's move to this one. So this one is simply A1 times this, the same thing. So we're also going to be using the dot product. So A1 dot this guy also. So the L with respect to W2, is it W2 or W1? Let's see. Yeah, W2 is equals to A1. Remember, A1 is what we computed here, which is this guy. A1, let's see, dot what? Loss with respect to Z2, okay? Which is this guy. Oh, did I copy? Okay, no question. So I think this I should probably transpose. Let's see. Let's check the shape. The shape of A1. The shape of A1 is 559 by 2. So let's check the shape of this guy, so we know if we are going to transpose or not. Okay, so this is 559 by 2, this is 559 by 1. Okay, so we're probably going to need to transpose the first one to be 2 by 559, so that this can go with this and we can have a 2 by 1 dimension. Okay, so we transpose A, or we can put this first and transpose it. It's the same thing. Okay. Great, that worked. So this is supposed to be a 2 by 1. Yeah, 2 by 1. W2. Remember our original W2. Here's our original W2. Original W2, which is this, is also 2 by 1, which is layer 2 and 1. So your loss has to be the same. Your derivative has to be the same. Okay, so we have that. Then for B2 is just simply the derivative, the old derivative for Z2, but it's going to be a single value. Remember the last B2, which is this guy, has just how many dimensions? Layer 2 dimension, which is just 1 dimension. So it's going to be having 1 dimension. So we're going to sum it together. Okay, so we can use the sum function. So the L with respect to B2 is equals to NP dot sum of now. How do you sum? Maybe I should do that here. This is the L2. That's 599 rows and 1 column. If I sum it, I'm going to having a single value. I'm going to be having a single value, and that will be my bias, which is this guy here. That will be my bias 10, which is this guy here for B. Okay, so we are done with that. Let's move over to the next one. Okay, hopefully this is not long. Okay, so the loss with respect to the Z1, which is this guy, we must compute the loss for ReLU, and the loss for ReLU is simply this. So meaning we have to do this first, then multiply the previous derivative, which is from A1 here, and this loss. So we have to write this, and that's pretty easy to write. So I'm just going to write a simple function called dReLU. Okay, so actually it's just going to compare the values of x. So anywhere x is less than or equal to 0, it's going to replace it with 0. Okay, and if x, sorry, small letter, is greater than 0, it's going to return 1. That's what we have here. Okay. So it's going to return x. So it's simply doing replacement. So that's the derivative. Very simple to compute. So we have this now. Then we can simply code this, which is just the previous loss with respect to a times the value we have from here. So I'm just going to go straight and write the L with respect to Z1 is equals to the loss with respect to A times, here's my times, I'm not going to be using time, let's see, okay, the value. Now the value of what? Remember the Z1 that was passed through here, right? So we're calculating the loss with respect to Z. Is this Z1 or Z2? Let me see. Yes, Z1 with respect to Z1. So good. Alright, this should work. Okay. So instead of writing this separately and doing, I just put everything in one line. We have that. Then move over to the last part, which is the final layer. So calculate the loss with respect to W1 and with respect to W2. So we have x times this and this. So the loss with respect to, okay, somebody is asking a question. He said, I don't understand the part you use sum. What is that line for? Okay, so for this part I use sum. Remember, the derivative of b2 with the loss with respect to b2 is simply the derivative with simply this guy, but this function is a 559, got it, it's a 559 by 1 dimensional array, but b2 from here is supposed to be just one dimension, just one. Okay, so if you sum it, you have to sum everything together to get that single value for b2. Okay, alright, now let's move. So we're calculating the loss with respect to w1, which is like the last layer, and that's simply x times the loss with respect to z1. Okay, so which is this guy. So you can see we are still chaining x, and x is what? Our value, our input value, which is this guy here, x. So I think that will be a dot product. So we have x dot. If you don't use a dot product, you are going to be having shape issues in this place. Okay, let me see. Alright, so I have that. Okay, then we do for the loss with respect to, I know this is the most complicated part. This backpropagation is the most complicated part, but the good news is that most of these derivatives have been computed, so you just have to just write them in code, implement them in code. So, and this is for a 2-layer neural network. That's why it's a little bit, that's why we have for A1, W1, W2 and the rest, and we have, this is supposed to be A1 or A2. Let me see. Oh, it's A1, correct. Right. That's why we're computing for 2 weight vectors, weight 1, weight 2. If it was just a single layer, then we'll compute just one. Okay, somebody is saying the video, yeah, the video will be shared after the class, so not so alright, so the last one, which is the loss with respect to b1, is equals to what's that? So it's simply equals to np dot sum, the sum of z1. Let's confirm. Yeah. Okay. Now I have to show you something here. Now if you look at the shape of z2, it's going to be 559. Oh, sorry. The shape of, let me comment this out first. The ReLU is not defined. How did I call? Oh. Matrices are not aligned. Okay. So you see, I think we have to transpose one of these. So let's transpose X. Okay. So I wanted to show you the shape of this guy. And this is 559. 559 by 2. Okay. So if you sum this up, if you want to sum a two-dimensional matrix up, you have to specify which of the axes you are summing. So if we have 559 by 2, for example, something like this. If you do np.sum, are you going to be summing along the rows? You know, if you sum along the rows, you are going to end up with a 559 by 1 dimensional matrix that contains the sum of this and this together, this and this together. But if you are going to be summing along the columns, then you are going to sum everything in column 0 to give you a single value, and everything in column 1 to give you a single value. And that is what we want to do, because for B1, the dimension for B1 is layer 1, which is 2. So it's a 2 by 1 dimensional matrix. So if you are going to be summing for B1, you are going to specify an axis, the axis to be, I think 0, row. So we'll do that. Alright. And that gives us all our derivatives. Okay? So we've done all this. Okay? So now, okay, let me quickly run through this. Now we have, what we did is we initialize our weights, which is this. Okay? We define our loss function, our activation functions. Then we did our forward propagation, calculated the loss, which is this. Then using that loss that was calculated, we did a backward propagation by calculating all the derivatives with respect to the loss, and that's what we have here. So if you look at it now, we now have the direction, because derivative tells us the direction or how we have to change the weight so that the loss will actually improve. So if we run through this once, run through the forward propagation once, and run through the backward propagation, we now have the tools or the values that has to be adjusted in the weights for it to move in the positive, in the right direction, so that our loss will increase. So how do we make that update? We make that update by subtracting the derivatives, which is derivatives of this, and this from the original weights that we initialized. Okay, so how do we do that? Here's my pointer. Okay, so let's update. I think that should be the next slide. Okay, so this is what I was supposed to explain before that part, where we have, for the training to take place, you have to run through the forward propagation, run through the backward propagation, then you update the weights and bias with the calculated gradient, which we have already calculated during the back propagation. So how do we update this? Okay, to simply update this is simple. So you take the weight, this is the weight we initialize, you subtract the derivative, which is the loss that we've calculated, the gradient that we've calculated, from the original weight. Okay, and you multiply by something called a learning rate. A learning rate just tells you what is the magnitude of this that you want to add to it. Okay, so if, for example, my weight is 1 and I calculate a derivative of, say, 0.5, okay, so if I subtract 0.5 from this guy, it will decrease W1. So if, for example, I'm decreasing in the right direction, this learning rate will tell you that instead of just subtracting 0.5, subtract, for example, if I set learning rates to 2, subtract 2 times 0.5 from it. Okay, so you can think of learning rate like something like this. If you have, for example, this is, let's say, this is your cost function, or this is your loss. If you plot your loss on a graph, you have something like this, for example. Okay, so if you initialize your weight at random, say for example, when we start the network, we initialize our weights to this point. Okay, So, and we are trying to get to this point. Okay, so how do we get from year to year? That is the essence of gradient descent or backpropagation. So we use our backpropagation algorithm. We calculate the loss with respect to this particular point. Okay, after calculating that derivative, we subtract it from this original weight. So if we subtract it, it actually goes down instead of going upward. So we go from here. Maybe for example, we subtract a little value, we jump to this point. We subtract another value, we jump to this point. Like until we do it over and over and over again, you can actually get to the lowest point, which is where we want. Okay, so your weight, your learning rate simply tells you that instead of taking small steps like this, you can actually multiply by a kind of magnitude that tells you how far to jump. So if I'm here and I specify a small learning rate, I can try to take little steps till I get to this point. If I specify a large learning rate, it can jump from here to somewhere here, somewhere here. So in the next slide, you can see that if you have two small learning rates, you have to train for a long time before your random weight can get to the minimum points you want to get to. Okay, but if you specify just the right weight, you can move with good number of steps until you get here. But if your learning rate is too big, you can overshoot and you start jumping about. Okay, so the idea behind it is that for us to update our weights, we have to subtract the gradient that we've calculated from the weights and save it back to this. So it's as if we are updating it, we are subtracting a small value from it based on what we have calculated from the loss function, and we are multiplying it by this learning rates. Okay, so now let's put this in code. Okay, so let's call this update weights and biases. Time is fast spent, so I'm going to kind of hurry up. Okay, so remember our weights are saved in params. So W1 will be equal to this guy minus so we specify a learning rate. Remember, we can also not specify a learning rate, but that would be bad. That would not be too bad, but the training will be slow. So I'm just, learning rates are typically small values, very low values. So I'll just specify 0.01. So we have this learning rates times the loss that we calculated with respect to, now we're doing for W1. So we do this for W1, W2, B1, B2. So we have B2, change this to B1. Okay, then I change this guy to, I think I call this W2. What did I call it? Oh, I use a capital letter. Okay. I'm just going to be consistent and use a capital letter throughout. Okay, W2, B1 and B2. Okay, so we are subtracting and making the updates. Alright, so let's run this guy. Okay, so we've updated our weights. Now if you look at the let's see, okay, so you can see these are the weights that have been updated. If you print the weights before training, for example, I'm going to initialize again. I'm going to initialize again, and I'm going to print the weights here first. So you can see these are the random weights that were initialized. Okay, so I'm going to train. I'm going to do a forward propagation, do a backward propagation, subtract, update the weight, then print it out again. So you can see I have 282 negative 0.09, and if you look at the initial weight, you can see. So the weight has actually been updated. Okay, so but now the idea is that remember, let's go back to the slide. Okay, so update weights and biases. So the idea is that you do a forward propagation, you do a backward propagation, update the weight and bias, and you repeat it for a number of times. Why do you want to repeat for a number of times? You want the weights to actually go down. So you have to do this thing multiple times, whereby you do a forward propagation, you calculate your loss, update your weights, you do it again. So if you do it for a high number of times, you can be sure that your loss function can actually decrease, because it keeps adjusting each weight and each biases. So meaning we have to repeat this for a number of times. So that is called the training time. Okay, so training time, just repeat this, for example, forward, backward, and the rest. So if I'm going to cut this and put everything in one cell, because I'm going to write a for loop that's going to do this for a number of times. Okay, so I'm putting this, I'm going to move this learning rates to where I initialize my parameters. Okay, so delete this. Okay, so for my forward propagation, I'm going to copy everything and put them in a for loop. Cut everything. So we're going to write a for loop that will run for the number of times you want to train. So for I in, let's say, range, I'm going to call these iterations. Then you do this. Okay, so iterations can be set. I can set this to say 10. Okay, let me do 100. So what this means is that this guy is going to run for 100 times, and for each of those 100 times is going to do a forward propagation, calculate the loss, and then do the weight update 100 different times. So we can see, so we want to see if the loss will actually decrease. So each time I'm going to create another variable called loss list that's going to be saving the loss for each of the iteration. Okay, so anytime the loss is calculated here, I'm going to append it. I'm going to save the loss for that particular iteration into this list. Okay, so let's run this. So if I run this for loop, okay, it's giving me some warning, divide by 0 a counter and the rest. Is actually because of the initialization. Okay, so let's look at the loss list. Oh, I'm having, wow, everything is 0, so probably making a mistake somewhere. It exploded. Oh, this is called I don't know if you are used to neural networks, there's something called weight explosion. Okay, whereby your weight explodes to infinity and your neural network stops learning actually. So you can see the weight has actually exploded. It is mostly, there are many causes of it. One is how your weights are initialized can actually cause this to happen, weight explosion. And another reason is because it's standardization of your data. Okay, because neural networks always likes your data to be standardized. Okay, so if your data is not standardized, it can actually affect this. So I'm guessing that's the cause of this. So we are going to standardize our data and see if we solve this. Okay, so that's why most of the time we hear people always say, before, if you're using a neural network, you should always standardize your data. Okay, so let's do that. We're going to use sklearn to do that. So from scaling dot, I think that should be preprocessing. Import capital letter. Import. I'm waiting for it to import standard scalar. Lazy typer. Okay, so we scale. This should come here. So we actually have to scale after splitting. What am I doing? We scale after splitting. Okay, so sc dot fit xtrain sc dot transform xtrain. Then remember, you should only standardize. Sorry, you should only fit your training data, not your test data. So your model does not learn the test data. Okay, so we scaled. So let's see if this will actually help our model. So we run this guy again. Still having that warning, but let's see. Let's look at our loss. None. So this didn't help. Oh, it was working fine, then it got to a stage, it exploded again. Okay, so let's see. Divided by count error. Okay. Another reason could also be, let's see, divided by length, np.sum. Okay, let me change the learning rate. Let me decrease the learning rates. Sorry, increase the learning rates. Then let me decrease the iteration to say 50, for example. Okay. Almost similar. Now we have just two. Okay, I think let's see, how is our weight initialized? Random and n 392 loss function and cos entropy. Okay, value update the weight. Okay, I think I'm going to. Okay, we scaled, right? Yeah, scaled. Most of the time, scaling actually helps, but it seems in this case, scaling did not help. So let's okay, so let me try increasing the number of layers here. Now you can see that I can easily increase this from 2 to 4 to any number. Why? Because I'm actually using the layer. I'm not hard coding it into this network. Okay, so you can see it's still going to reference 4. So let me try and increase the layers first and see if this guy won't explode anymore. Same thing. That's weird. Okay. There are lots of things that go into, actually optimizing most of these libraries that you use. So these are some of the issues that actually goes there. There are lots of optimization they use in terms of how the weights are initialized and the rest. So I'm going to okay. Maybe I should decrease this a bit. How about using minimal scalar instead of standard scalar? Okay, it's actually different. Standard scalar takes your value to between a range of 0 and 1. It's actually good for neural networks. Minimal scalar you can actually specify the scale that you want to use. So you might decide to use a range of between 5 and 10. So it's between a minimum and a maximum value. So I think standard scalar is actually, kind of better for that. Okay, so let's try. I increase the It didn't actually explode this time. Okay, let's look at the loss. Better. So what did I actually do? I decreased the learning rates. So you can see that if you come back to this slide, sorry, yeah, so this is actually what happened to our network. The learning rate was 0.01, so it was actually too big. So our network actually overshoots the learning point and went to infinity. Okay, so you can see the importance of this value. Now you see the reason why they normally set a learning rate and actually like to scale your data. Okay, so and also your loss can also, your weights can also explode when you don't scale your data or when your weights are not properly initialized. So that's why sometimes if you initialize your weights to 0, it can also cause this issue. So we don't know if the weight is decreasing. Okay, it's kind of decreasing. I'm saying from 3.4 is going to 2.8. You can see with time it's decreasing. So it will be better if we actually increase the number of iterations. But before that, I want to just plot this function so that we can get an idea of how the loss looks like, because it is supposed to be decreasing. So I'm going to use period. Okay, so now you can see the loss went starting from 0.35 actually to 0.29. So there's also still room for improvement, so I'm going to increase the number of iterations to say 100. Let's see how far it can get to. Better. Going to up to 0, so going to almost 0. Good. Okay, so we have that now. So meaning this works. So this is the training phase. So you can see that for each iteration, it goes through the forward propagation, computes the loss, goes through the backward propagation, which actually computes the derivatives that you want to add to the weights so that it will be updated. Then you update the weights and biases, multiplying by particular learning rates. So you can see that the loss actually decreases on each iteration. Okay, so now so making predictions. Okay, now so we've done forward propagation, we've done backward propagation, we've written our for loop, we've trained. Now you remember that after training, you are going to be having after the number of iterations run, you're going to be having your optimal weights and biases for that particular training. So if you want to make predictions, you are going to be using these weights and biases that have been calculated after the training. Okay, so to make prediction, you simply do a forward propagation, a forward pass through the neural network using the calculated weights and biases. How do you do that? So what you simply do is, so what you simply do to make prediction is to do just the forward pass, just this. Your y-hat becomes your prediction. So there's no need to calculate the loss or do a backward propagation again. Why? Because you are going to be using the updated weights. You can see these weights here are the updated ones you have calculated from the iterations. So you are going to be using the updated weights to do this, compute these functions. This becomes your prediction. So now let's copy this and create our, that's actually the part 2. We're supposed to take a break, but there's no time, so we'll quickly just move on to that. So I'm going to add it behind here. So I'm just going to create a function called predict. Predict will take your, for example, the values we want to predict. Let me call that x, and do a forward propagation. Forward propagation in the sense that it's going to take the calculated weights, multiply it with whatever you pass through it, add the parameter b, then call the sigmoid function and make a prediction. So this will now be your prediction. So but remember, sigmoid is going to be giving you probabilities. Okay, so please note that. So I add. So now let's use this predict function. I'm going to call it on, let's call it on Y train as well. Okay, so it makes the prediction using the calculated weights. Let's see, let's look at the prediction. Aha. I'm seeing 0 0.99, 0 0.99, 0 0.99. Probably predicting 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh, this is too long. Probably not doing well. Predicting 1 for almost all the classes. So let's see, for 6, let's print 6. The first 6. Aha. Okay. Then let's look at the true values. Let's look at the true values to 6. Oh, okay. So it's 0.9 for this guy. So I'm going to convert them to integers, or you can round them up. It's an array. np.int. What am I doing? Okay, I think I'm going to do that here. np dot should I use int or round? Int or round? Okay, let me see. Aha, sorry. Round. Okay, still no question yet. Fed to 6. Okay, so it's predicting 1 1 1 1 1 all true, and it's having 0 1 0 1 1. So it's probably not too doing well. So let's look at the accuracy. So I'm just going to write a simple function that will calculate the accuracy. Accuracy takes the y and takes the predicted value. So I'm just going to return, no, let me just create an intermediate variable called ACC. So I'm going to be having where y is equal to y at. So remember, these are going to be arrays. So if it is equal, we sum it the number of times. So np.sum, where y is equals to y at, divided by the length. So we want the average, divided by the length of y, then times 100. So it puts everything in its own bracket, times 100. So this is just this simple thing. Yeah, that should be it. Sum np.equals to what? Okay. So let's look at the accuracy. So we call this accuracy. I'm just trying to prediction, which is okay. Y train and threads. Okay. Oh, I didn't return this. Return ACC. Okay. 34%. It's doing bad. Okay, I think let's increase the training time. Let's increase the training time to say to say 200. So I'm just going to, here's my runtime. I'm going to restart runtime, clear everything, and okay, no question. So I'm going to run everything from the beginning. Okay. Alright. Shape, all good, neural network, params, train. I'm having divided by 0 again. Did I decrease the learning rates? Yeah, I did. Okay, so let's try to plot the loss. Okay, let's make a prediction and see the accuracy if it actually improved. 0. That's bad. So probably it didn't learn. So I think I'm missing something. There is a calculation we are missing. Maybe a sign. Let's see. Sample length of x. I'm coming. Quickly going to check. Okay, we scaled. Random seed. Blah blah blah. Okay. We are missing something. Probably a sign. Sigmoid plus neural network. Okay. How good. Added the axis. Okay, we added the axis to this. Did we? I'm just still going to add it here, just in case. Okay, looks good. W1, W2, B1, B2, P1. Everything looks good. Okay. So I'm just going to change the seed. Then probably take this one to 5 and see if that helps. Number of iterations. Let me start with 100. So forward propagation, value, y-hat, gradient, then the update. Okay, let's see. Still at Sonia and Su. Probably not still doing well. Let me decrease the learning rates. I'm going to make it very small. Okay. I think the problem is probably coming from the learning. Still not doing well. That was weird. Let me see. $31. Quite low. And the one I have here is actually doing. Am I calculating this thing proper? Oh, I wish I'm calculating this thing properly. Okay, I think I'm going to bring this one I did here. Over here. Plus will be x dots. Yeah. Okay, so if you have questions, don't forget to ask. Hybrid is not defined. Why add mental? 31. Okay, it's actually the same thing. So probably our training. So let me take this to 500 iterations. Learning rate stays the same. Decrease this. Probably going to use Let me go little 3. I'm going to run it again. You can see the error actually decreases on each iteration, so it's probably because of the way the weights are initialized. So I'm going to remove the random state. I'm going to remove the random state. Run this guy from the. Yeah, if you have questions, I'm seeing somebody typing hello. If you have questions, you can always ask. Yeah, did that. I'm going to restart this kernel. Yeah. Okay. What's the time? 1:35. Wow. We have like less than 30 minutes to go, so I'm just going to quickly run through this. Oh, I've done on the other side. I've done all before. My cost entropy is okay. I think the problem is not from there. Let's see. Okay. All right. Zero point 0.01. I'm going to. There is some. Okay. So I'm going to do some tweaking. So you can likely call this parameter tuning. Good job, Isaac. Please, why is the loss plot showing the reverse? So that seems to be increasing with epochs. Yeah, it's supposed to be in the other way around. Yeah, so probably is the way our network is training. So I think the reason is that our weights are exploding. So it's from decreasing, so you can see it's going to none. That's the reason why. And the problem is probably coming from where we initialize the weights. This is 0 and 1. Yeah, I think it's quite okay. W1, W2. Let's see. Okay. Yeah, I'm looking at my previous, the one I did yesterday, and it's basically the same, but I didn't get this error. Okay. That's the thing about live coding. When you start live coding, you start getting some kind of funny errors. That's okay. Max train. Okay, I'm going to bring back that seed again. Random dot seed. Okay, so let's run these guys again. Cost entropy is okay, looks okay. Times this, okay, return. Yeah, you're correct. It's supposed to be the other way around. Forward prop looks okay. Okay, cost entropy, loss, finite cost entropy, y at loss, yeah, well, this looks good. Still having the same issue. Our weights are exploding. And it's probably normally that's weird. Okay, if we look at, let me see, I can copy the one I did here. I'm going to copy the one I did here and actually try. And actually, I'm going to use it here. So it's basically the same thing for what we did here, 941000 and the rest. So I'm going to try it. Okay, run successfully. Trained for 50 epoch. So where did I make the plot? Okay. So plt dot plot cost list. This is working well. So what is the problem? Basically did the same thing. Okay, X train, Y train, cost list layers, we use 941. Then it is 0.01, parameters W1, W2. Okay, so basically the same thing. Initialize our weights, calculated the value. I know the problem are we coming from, maybe we are missing a particular sign. Okay, so this is this plus this. So let me compare with, yeah, it's this guy. Okay, 1.0. Basically the same thing. Okay, so cost entropy, number of samples, length of y. Okay, that's fine. Wait, the length of y. Yeah, same thing. So minus 1 times the sample times this, which is what we did. Can I remove this one? Then number of iterations, I had coded it here to 50. Feed forward prop, basically the same thing. Append to the list. Then we did the backward prop, which is the same thing. Now updates the weights and bias. And this is running fine. So we're probably missing a sign, and because this is live, I think that's why. So you can see this is actually decreasing well. Actually went to 0. Let's predict. Prediction, what did I call this? Okay. Let me see. Yeah, predict. So, okay, I think I'm probably going to move this guy so that, because I'm going to be sharing the notebook, I'm going to replace it with this guy. Yeah. Okay, so we have this. Now I'm going to clear the runtime to start it all over again. Hopefully it works fine this time. But I believe you decided to get the idea behind why we initialize the weights the way we do, why we set the learning rates, and the layers of the network, how they actually help the network. So I'm also going to remove this because everything is in that single function. So I'm going to remove this. Yeah, so I have this. Okay, so now let's run before. Almost 2 o'clock. Wow. Okay, so our network is in order, so I can oh, no error. Okay, so what do we call our cost? We call this cost list. That's where we are saving our cost to. It's not in the right place. So I can probably make predictions with this now. So let's predict. Params is not defined. Sorry, I called this NN params. And we actually changed it. Okay, so we made prediction. Now let's look at the accuracy. 97. So the problem was actually with we probably missed a sign in our network, but so far everything looks the same. It actually works. So we had 97% accuracy on the training. So let's use it to predict for the test sets that we've not seen before. Let's see how well this guy is doing. Okay, test. I'll call this thing test thread. Okay, I'll calculate the accuracy of the test prediction. So remember to change this to iTest. Oh, you can see 95%. So it's doing so well, very well in this task. So we have 95% in our test sets and we have 97% in our training set, which is quite okay. So you can see with just a 2-layer neural network, we were able to make a prediction on breast cancer and to see if someone actually has benign or malignant cancer. Just have a 2-layer neural network with 4 hidden layers. So let's look at the did we plot the loss? Yeah, we did. Okay, so we did. Okay, so maybe for example, if we try to increase, let's increase the number of the training time and see if it will improve our prediction. So increase the training time. Didn't improve. 97, still 97. The test set still remains the same. Okay, so maybe we can try increasing the architecture to say I'm going to use 10. Let's see, probably overfit. So I'm going to use 10. Okay, so let's see, 97. The same thing. So it's this actually went down. So under fitting. So you can see that's where your hyperparameter tuning comes in place. So you can do those tunings. So I'm going to take this back to 4. Now, alright, so let's go back to this. So we've done the making prediction. And we're supposed to have part 1 and part 2, but there's no time, so probably just quickly move. Now I was supposed to do this, because what we wrote here is we actually wrote everything in a kind of functional way. We wrote a for loop, backpropagation, everything in one step. So now, as soon as you run this cell, everything runs. So I wanted to actually design it in such a way using OOP, so that you can actually call it like the way you call your keras or your sklearn.fit, and it performs every function. But I don't know, it's 1:48, so there's probably no time to do that right now. So but what I would do is I have the notebook where I wrote this. I took this function. It's practically the same thing. So what I basically did is just to rewrite these guys and put it in a form of like a standard API. So I think I have it here to copy in a standard API format, so that you can actually just, instead of running each cell, you can, like, it's like your mini deep learning library. Okay, so this is the code. I'm going to paste it here. So it's basically the same thing, but you can see I'm putting it in Python class, and you can see I have my neural network class. Okay, so now this is the initialization, where you have the layers, the learning rates, the params, cost, the number of iterations, your training variables. Then there's a function called init_weight that's just I'm basically just taking from here and just rewriting it in OOP formats. Okay, so you initialize the weights, relu. Now you can see there's this underscore before each of these functions. It's just telling you that these are private functions, that you don't have access to them. Okay, these are class functions. Okay, so I have value, sigmoid, cost entropy, forward propagation. You can see forward propagation is not having its own function, backprop is having its own function. Then you can see this is the fit function. So this is the function that you can see, that you can call after creating the class. So you call this fit function just like your sklearn.fit, pass in your training data set, and it automatically goes through the number of iterations that you've set, calls the forward propagation function, calls the backup propagation, also append the cost. I also added this to make a prediction, this function to plot the loss, and this to give you accuracy. So how do you use this? It's very simple. So this is how you use it. How do you save the model? Somebody is trying to save this model. Okay, you can actually save it by serializing it. Okay, but for now you can just use it like that. Okay, so you can use it this way. How do we do that? You can just come here. If I run this cell, now you can use it like your normal libraries. Okay, so I can say my network is equal to, the name of this class is neural network. Okay, so you can see it has layers, learning rate, iteration. So I'm just going to leave everything as their default value. Okay, so I initialize my network. Now I cannot call, if I run this cell, I can say my net dot. Okay, now you can see functions I can call: accuracy, fit, plot loss, predict. Now you can see those sigmoid, relu, they are not available to me. Why? Because they are class functions. I actually made them invisible. So because I'm placing an underscore here, that's Python's way of hiding these functions. Okay, so it's basically like your normal libraries. So if I say dot fit, it expects the training data and test data. So I can pass x train and y train to it. If I run this cell, so it fits the data for me. Now how do I predict? My net dot predict. What am I predict? For example, I want to predict on S test. I call this predict. So you can see it's basically easy to use now because I created it in a class format. So these are my predictions. Oh, I'm not going to scroll through that. Okay, so what are the functions that are also available? You can do my net dot, I think there's accuracy. Yeah, accuracy. Oh, sorry. I'm going to need to pass in the prediction and I test. Preds and y test. So you see 95%. Then you can also plot, which is my net dot plot loss. Can you use NumPy conveniently for deep learning, or there are some limitations at some point? Because I have none of patterns of this, I'm trying to relate. Yeah, I think most people don't get what we're trying to do here. What we're trying to do here is not to create our own network that is going to be replacing PyTorch and TensorFlow. The idea here is to better understand how these things work. Okay, so the what TensorFlow does, TensorFlow is actually like NumPy, advanced form of NumPy, that gives you building blocks to build your own neural networks. Okay, so you can actually use TensorFlow to do basically everything I use NumPy to do in this place, but Keras has been created. So Keras is like a library on top of TensorFlow that has done all these things I'm doing here. What we did here, this fit, backprop, forward prop, Keras has abstracted everything for you so that you can now call your Keras, use Keras in this format where you can say .fit, .predict, .accuracy. This is what they've done for you. They've abstracted everything away. So the idea behind this tutorial is to do these things by yourself, do these things from scratch, and like see and understand what is working behind it. Okay, so that's just the idea. So PyTorch, TensorFlow, they are the same thing. They are doing the same function, just trying to abstract away all the low-level stuff. Okay, so you can see we plot our loss function. So we basically just took our functional code and put it in a form of like a class function that you can initialize this way. Okay, so that's then okay, we've written that code, testing, we've tested and plotted some charts, we've done that, and so extra improvements before we round up. I think it's almost 2 o'clock. Wow, 5 minutes, I have 5 minutes to go. Okay, so it's almost 2 o'clock. So better weight initialization, I added some links here. Now there are different types of weight initialization. There's the, you can initialize with 0, you can initialize randomly from a normal distribution. There is the E, there is something called the HE initialization. There are different types of initialization, and they can actually help training and help your model better train. Okay, you saw the issue where we are having exploding gradients and exploding weights. Those can be caused by the way our weights initialize, and maybe probably a bug in our calculation. So somebody said, can you also implement this using TensorFlow or Keras so we can draw comparison? Of course, yes, we can. We can implement this using Keras. We can even implement this using scikit-learn. So it's basically the same thing. What we actually did, basically almost the same thing. But if you're going to be using Keras, you're not going to be doing this ReLU, sigmoid, cross entropy by yourself, forward prop. You're not going to be computing gradients by yourself. You're basically just going to be creating a network. Just create a network, just like something I did here. So you can just say from TensorFlow.Keras, import models, create your model, and pass in your train and test sets. Specify the type of loss you want to use, which is binary cross entropy. Then do that. You are not going to be doing these calculations by yourself. Okay, this is just to like give you an idea of how it works. Okay. So you can also do something called stochastic and mini batch gradient descent. Okay, so what we did here is we went through what we did in the fit. Yes, that fit. Okay, is to go through each iteration and compute the loss using all the data points. So for stochastic gradient descent, you use just a single data point. So you compute the loss based on just a single data point. So then for mini batch, you can cut your data set into batches and try to use that to make your gradient descent or do your back propagation. Okay, so I actually implemented the stochastic gradient descent here. It's the same thing. The only difference is going to be in the way we train our data. So everything is the same. It's just the way we sample our data points. So I'm also going to add that to this notebook so you can actually still go through it. Then what other improvements? Learning rate scheduling. Now you can see our learning rate was fixed, and if you saw what I was doing earlier, where I was trying to like change the learning rates depending on the task. So most deep learning algorithms have different types of learning rate scheduling, whereby the learning rate can adapt. So it can actually start from a particular value, then as the training goes on, it start decreasing to help, like it adapts to your training. There are different ways to do that. You can actually code these things by yourself. They are pretty easy to learn. Okay, and it's been a really long class. So in summary, to create a neural network from scratch, you just need to get the input data and the target. So you know the number of features. The number of features will determine what the starting layer is going to be. Okay, so you can see in our case we have 9 features. So we have 9 in our input layer. Okay, then you initialize your weights and biases. There are different methods, but we decided to use a random initialization, which is what we did here. Initialize our weights randomly. Then we compute the forward propagation. Forward propagation is simply just the weighted average, then you pass it through the activation function. So this is what we did here for x. Add the weights and the bias, activation, passing through the sigmoid, then you calculate the loss. Okay, then you compute the backward propagation, which is what we have here, or the gradient with respect to the loss. Then update the weights and bias. So we did the update here by subtracting the gradient from the original parameter and multiplying by the learning rate. And finally, you repeat for a number of times. So that's where we did our fit, thing as a fit, yeah, for the number of iterations you want to run so far. Okay, so that's basically neural networks. I know there are lots of many questions, many things that are not that you don't understand, but I think you can actually go back to the video over and over again and just try to get some parts. If you don't understand, you can always message me, you can always search on Google. Also get more books on neural networks to read about. And I think most of the time these things will become clear, because I think when I was trying to do this at first, I think that should be like 2018 when I was trying to do this at first, using Andrew Ng's tutorial on Coursera. I was trying to implement these neural networks. It was very difficult, I must tell you, to understand this, to understand the weights, the bias, shapes gave me gave me serious issues. So these are not things that you learn in one day. So you can just keep practicing it and doing it from time to time, and you surely get it. And I would advise you to always just try to implement this from scratch by yourself. At least just try to do it from scratch by yourself. It helps you better understand how these libraries work. So if you have questions, you can use the live chat session. I'm just going to wait for 5 minutes and see. This is 2:01, it's supposed to end by 2. So questions and extra links. Then so for some more information, the notebook is going to be shared. I'm going to like put everything together in a correct format. I'm going to share it as a mail after this class. Probably you get that mail towards evening, maybe 7 to 8. Okay, so I'll share the notebook, I'll share this slide also. Then the video will be available, I think maybe in the next 48 hours. Just have to do some maybe little editing, so the video will be available. I think that's it. The video will be available, the slides will be available, the notebook will also be available, and I'm also available for questions and answer. So you can follow my Twitter. I'm always active on Twitter, so you can probably message me on Twitter, send me an email, follow me on LinkedIn, and we can keep the conversation going and chat from there. So somebody is saying, how can this be implemented with a web page to make a prediction with a web page? Wow. Okay, so if you are going to be implementing this in a web page, I would advise you're probably going to be using optimized libraries like your Keras, TensorFlow, and PyTorch, and the rest. So you're not going to be doing this from scratch on your web page, but it's very, very possible. You can actually do that. So it's a wrap up for me from here, from Data Science Nigeria. So also don't forget to follow Data Science Nigeria. Get information from time to time. We'll be having webinars like this, I think so, from time to time. So make sure you follow Data Science Nigeria on Twitter, and you can get information from there. So thank you guys, and I'll see you around. And stay safe, stay indoors, and stay safe. Bye.